Great. Thanks, Steve. So we're all really excited to give this presentation. Like Steve and TJ were saying, that this is being recorded. And to me, that means that this will be a resource to you all in the future, because the next 4 hours is going to be stuffed with quite a bit of information and knowledge. And we're really happy to put that forward, but it's going to be probably all too much for everyone to absorb all at once. And so what we think is that, by recording it, by creating this detailed catalog of information in this recording, that we hope it to be a continued resource into the future. So just want to say that up top. Another thing I think worth mentioning is that the expectations for today is really just to introduce Sustain as a model and how it works as a process-based simulator, and give you all the foundation to begin to be modelers. And so we find it really fun and interesting, engaging, and challenging. And we hope that we can kind of impart that to you all today through this agenda that we have. As far as taking and handling questions goes throughout the presentation, I think it's best if we try and keep them more towards the end of the presentation, or at each end of each of these exercises. That'll help, I think, streamline the whole process. But with that being said, if there's something that John or I or Steve are being unclear about, or we're not giving enough time or attention to describe something on that particular slide, I think that's an okay place to kind of use the raise your hand function, and we're going to be looking out for that. So if we miss that, TJ, let us know if someone's raising their hand on a particular slide, and we can clarify whatever we're being ambiguous about and then move on. With that being said, I'm going to go through the agenda. It doesn't seem like a lot, but 4 hours is going to go really fast. And so we've got a set of objectives for us that we want to kind of go through today. It keeps us, to me, on track with what we want to do. So we're going to go through that first. And then the next 4 bullets is really the meat of the presentation, where we're going to introduce Sustain and where it sits within the WIMS 2.0 framework. As most of you all know, we Paradigm updated with County Public Works, the WIMS modeling framework, and Sustain kind of sits within that. And so this will help give context of where Sustain is as a model within this model framework. And then we've broken down the Sustain training into 3 exercises. The first exercise is just preparing the model. What do you need to do as a modeler to get the project, whatever project you're modeling, set up? And so that's GIS work, runoff time series, characterizing your BMP, those sorts of things. The second exercise is getting the model itself ready. So getting that input file ready, configuring the folders, making sure you have those pathways right. And the third exercise is actually running it, hitting execute, and then looking at your model output and seeing what that looks like. So that's kind of a big picture for the day. And then there is a little bit of extra bonus. So depending on how much time we have at the end of the session, we may be able to get into this exercise 4. And so there's going to be a lot to unpack in these first 3 exercises, and whatever time remaining, there's all sorts of additional functionality and useful things that we can get into in this 4th exercise that I hope we have time to get through quite a bit of it, but we're going to play it by ear and see how much we can do. So that's our agenda. We do have kind of these set of objectives that we want to put up front, just to put us all on the same platform for what we're about to get into. And the objectives are: 1, understanding Sustain just as a model. It's process-based BMP model, and we'll get into what that means. But if we can help everyone to understand what that means and how Sustain operates in broad terms, that's our first goal, is to be able to do that. And then once we've done that, having you all be able to prepare a Sustain input file for simulation. So to do that, you would need to be able to run LSPC to generate an input time series, configure the necessary folders and files to get that run ready, and then adjust input parameters to match project design. And so a lot of that, if you're not familiar with Sustain, might sound like French so far, and that's okay. It'll make sense if you rewatch it again at the end. But I think by the time we get through this, hopefully everyone will know what those things mean and how to do those things. Second to last is being able to troubleshoot common errors. For anyone who's modeled LSPC or any other program, there are a lot of challenges and issues that come up when you're running something, because there's so much that's going into these models, and there's a lot of little things that come up very often. And so we'll go through our list of things that we are common issues that we feel like that we come across a lot. And hopefully by sharing those with you, you all can kind of understand those so that you don't have to hit those speed bumps as often. And when you do, you understand what to do and how to overcome them. And then lastly is being able to display and interpret the results from Sustain. So as you understand Sustain as a model, are able to run a simulation, move through the process, and overcome any errors, you want to be able to look at the output and understand what it means and make sure that what the model is telling you is correct and reflects the parameters or the project at hand that you're wanting to put into Sustain. And so that is our so these are our objectives. Steve, John, anything else you two want to add to kind of this big frame up of what we're going to get into?
I think you've covered it pretty well.
Okay, great. So with that, there's a little bit of pretty brief background that John's going to get into. This is really just setting up the kind of the space for us to talk about Sustain. And so we're not going to get into too much of WIMS and where it sits within, or where Sustain sits within WIMS, but I'll let John kind of explain WIMS over the next set of slides. John, it looks like you're still muted. Still muted. Not working?
You'd think we'd be Zoom experts by now, right?
You got it.
Every meeting without C's, there's always something like that. Oh, you're muted.
Yeah.
All right. Well, yeah. So LSPC, Sustain, and how they fit within the WIMS framework. LSPC is the watershed modeling system, as you know, and it is the one that does the rainfall runoff simulation. It also has the routing through the stream network. So all of the in-stream prediction of hydrology and water quality is handled there. Sustain is the piece where we then take a boundary condition such as runoff from a particular sub-watershed as an input to a network of PMPs, and then we can run an alternate runoff scenario from the baseline that can be used to look at other management questions. But Sustain does do the simulation part, but the key part of it, which makes it really adds a lot of value to this, is the cost-benefit optimization that it provides. And so, as we go through this, we'll look at that, and we'll talk about the processes that are involved. As Ryan mentioned, it is a continuous simulation model, process-based, and so you'll see some of that in the texture in the next few slides. All right, so here is a generic schematic of the components of LSPC. This is the original WIMS 1 framework, but the framework is similar in that you have a GIS interface that's used for launching the model. There's an access database in the background that is where all of the relational information about subwatersheds, attributes, parameters, network connectivity is stored. And then the LSPC interface for the model itself talks to the database and represents whatever subset of the study area that you're interested in simulating. You can generate an instance of conditions for running and simulating that runoff and water quality as well. So we talked about process-based simulation in SUSTAIN. So SUSTAIN, the acronym stands for the System for Urban Stormwater Treatment and Analysis Integration. It's a model that was developed by EPA ORD, and I had the privilege of being part of that development team. And in the context of that, it is a dynamic simulation model, and it looks at all of these key processes that are illustrated here. Runoff comes in as a boundary condition, as is evapotranspiration or potential evapotranspiration expressed as a boundary condition. The model will take the runoff, fill up the storage that's been defined. Depending on what processes are involved in the BMP that's being simulated, you can have settling, filtration, absorption, passing through soil media, infiltration, and then ultimately when you have exceeded the capacity of the storage and the soil storage potential, there is outflow from the BMP. And so in the context of SUSTAIN as an optimization, the size of that footprint can be changed. And as you change the size, there's a unit cost that is also associated with the changing footprint of size. And so that's where you start to have the building blocks for building the cost benefit optimization. And imagine this simple model for one case repeated 100 times for all the opportunities that you have in the watershed. Now, when you search through all the combinations of size, footprint, configuration, whether or not it's even there, that's how you start to build the building blocks for generating those cost effectiveness curves that you've seen in some of the RAAs.
John, one thing I was going to add is that I'm getting some feedback. There we go. One thing I was going to add is that, this is, like you said, a dynamic simulation model. And if you want to model what to me looks like in this slide is some sort of like sand BMP or media BMP, sand filter. If you want to say, well, I want that to be a bioretention cell, that's just a matter of adjusting or changing parameters within SUSTAIN, which we're going to show people how to do. So, if I want to turn on, if I only have evaporation right now, but I want that to represent evapotranspiration from plant processes, that's just a dial that we add. And so we can add that. We can also add an underdrain. And those processes can be, or bioaccumulation, biotransformation, phytoremediation. We don't necessarily have knobs or dials for those within the model, but you can simulate their effect by adjusting parameters. So just adding that, a little bit of that for how to adjust and dial in processes.
Yeah, that's right. Thanks, Ryan. And yeah, as you see, it's we think of it like a Lego box, right? So you put the pieces together that you need to represent the construct that you're trying to simulate. And so if you have an underdrain, you can tack that piece on at the bottom. Now the system has some guidance to kind of step you through what types of opportunities, because really the opportunities, it's limited by your imagination and how you can construct these things. Some of the processes that are listed in here sound pretty involved. Now the model is not going to be simulating phytoremediation, but for example, if you have laboratory information or a case study where you have what that process looks like in terms of the time of decay of a pollutant, for example, or the filtration rate through a soil media, or you have the final effluent concentration through the underdrain. Those are the types of information which are usually commonly available or that you can monitor in the field. SUSTAIN gives you a way to put those in to represent those complex processes. So, you know, in that sense, it's this balance. You don't want to have a model where you have all of these knobs, because then you get into this danger of trying to overtrain it. But it's best described as more of an empirically informed, process-based simulation model. All right. And so what we're seeing here is a schematic, beautiful graphic that Ryan Edgley has put together. Just these tabs represent the different parameters, soil media, for example. These are the actual parameters that go into the model. So if you're representing a bioretention basin, you would need the depth of the soil media. You'd have some kind of infiltration rate and wilting point, porosity, depending on what infiltration method you're using. Some of these terms become more or less important. If there's an underdrain layer, you specify the depth for that. So think of it as you specify the profile for this BMP. And so this profile is sort of locked in place. And then the other dimension that is going in and out of the screen, that is the length, the size of the BMP. So that's the variable that Sustain would optimize during the course of the simulation. Or if you already know the size of it and you're just trying to represent its response, then you put that length in and then you simulate that response. So all those functions are available. And I think there's a couple others in this animation series.
Actually, I took those out to save us time, John.
Oh, okay.
But I was going to add, because we don't have all those, there are all these BMP types on the left-hand side that we parameterize with design specifications for WIMS 2.0, and there's a phase 2 report that has all those details. So to kind of keep this portion of it contained, we'll kind of point people to that link if you want to see all those other BMPs. The idea here is that if you're going to model bioretention, that you don't have to think about all of these details. You can kind of take this off the shelf and say, well, this is kind of representative of a bioretention cell type within LA County, and you can plug that into your model. And if you want to change depth from 36 inches to 24 to represent, specific depth that you know about that might be implemented there, you can make those changes in Sustain, and we'll show you how to do that. But this is kind of a little bit of shopping. If you want to do porous pavement, we would just recommend you go to the WIMS this report and look for those design detail specifications, and you can port those into the model, and we have the citations and sources for that. So it kind of just sets you up here for that.
Awesome.
And then here, this is just showing actually we have an interface for WIMS 2.0. There's a website, and we have a link on some of these pages. But this just shows the repository for data and documents and downloads. And so the phase 1 report, if this was an actual interface on the website, I can scroll down here and I can click that phase 1 or phase 2 rather report and download that. And that's a PDF, and that has quite a bit of information about Sustain and where it fits within the WIMS framework. And then one more slide here about the WIMS website. We're not really going to go through the optimization framework per se, but there are some places that we'll be pointing to people or to you all to get data, and it's actually in some of these utilities. And so this also exists as a optimization framework. We're not focusing as much on optimization in our presentation. We're really focused on kind of the single solution, but there is this whole other world and side of things. So just kind of point that out because we will be referencing it later. Okay, so that kind of concludes the first part of just setting us up. And so if there's any questions, I think it's probably a good time to raise a hand, and we can address some of those things now as it pertains to those slides. And then if there's nothing, we're just going to get right into the first exercise, which is going through model preparation. Okay, so I'm not seeing anything, so we're just going to jump into it. Before we get into the actual slides, When I first think of, if Steve or John comes up to me and says, "Hey, Ryan, we need a model. Here it is. You take this and go." I kind of think to myself, all right, well, what are the first things I need to do now that I've got this new assignment to create a sustained model? And those first three things for me are what's in exercise 1, which is I need runoff in my model to simulate, stormwater happening during storms. I need to understand the hydrologic response units, what we call HRUs, upstream of it, upstream of the projects. How much roof is there in the drainage areas, how much road, front lawns, which would be like short vegetation. What are the soil conditions? Is it hydrologic soil group A, B, C, or D? These all impact runoff. And so knowing that from an HRU perspective is going to inform the model. And then lastly, what does my BMP look like? Is it a bioretention cell? Is it an infiltration well? That's going to inform what we do in the input file and how we adjust those parameters, and ultimately inform what the solution looks like, because 100 dry wells in the model will have a different output than 10 bioretention cells or one big regional infiltration facility. And so how we think of that BMP gets translated into the sustained input file. And so for me, these are kind of the first three things that I think about if someone's going to give me an assignment to build a model. All right, so with that, I always want to know, where I am, what we're doing, and what does the project look like. So what I'm showing here on the right-hand side is the project that we've selected for these three exercises, which is this East LA median project that you all are working on as a team, or certain folks are working on as a team. And so, if Steve comes up to me and says, "Hey, I want you to work on this East LA project," my first thought is, well, where is it? Where is this specific location of where that footprint is, and what's the upstream drainage area? Those are the first two things. So I feel like I need to kind of get myself immersed in where we are, but also start to feed in some of that information about hydrologic response units and drainage area. So that's what this is here. The second question is, all right, well, I know where we are. I need rainfall. I need runoff, and that's where we're referencing the WIMS 2.0 website here. There's a weather utility here that has what we call a subwatershed gauge assignment shapefile, and I'll show what this is on the next slide. But what we're showing here on the right-hand side is a weather utility that's available at this URL link. And on the right-hand side, there's a button that you can select that will allow you to download a set of geospatial data. And what this does is it shows the meteorological zones for all of LA County for the WIMS model domain. And so if you can think of, rainfall in Los Angeles, there's going to be more in the San Gabriel areas, less in the coastal basin area. And there's, all sorts of heterogeneity in terms of where precipitation is on any given storm. And we capture that in this set of meteorological zones. So let me flip to the next slide. And I've got that same image we had before showing the drainage area, but now I've popped on these meteorological zones. So that's what these kind of pastel colors are, showing the different zones for precipitation. And so you can see that a lot of the drainage area is this P391C_3, and you don't have to worry about what the numbers are. That's less relevant. But that's how we've named these things. There's a whole naming convention associated with it. But it's mostly this green one here on the right, to somewhat lesser degree, this other one, D1277. And then, actually, I've got some squares on here. We got a little bit up here, pink. We got a tiny amount of D1277 there. And then we have a little bit of this, this P391. And so if I'm going to get ready to run LSPC to generate runoff for these precipitation files for this particular project, my first thought is, wow, that's a lot of precipitation files. It'd be really easy to deal with one instead of 5. And so there's two approaches, and John, I'll have you in on this too, but there's two approaches to handle this. We can take this precipitation file and we can assign it to the whole area. Or we can kind of mesh these together. And so if this is maybe 55% of the drainage area, this is 30%, this is 2%, I don't know, this is, so whatever makes up 100%, we can do an area weighted composite of these five precipitation files and create one from it. In most cases, that's probably not necessary. To me, we're in a pretty, well, there's a couple of things. One, we're in a pretty small area. We're not doing, LA River Basin or St. Gabriel River Basin, which does have tremendous variation in precipitation patterns across that area. We're in a pretty small area. And if I looked at this precipitation file for this green area and this yellow one kind of side by side, if I looked at that time series hour by hour, probably not going to be very much variation in those time series. What you could do if you wanted to kind of feel more confident about a decision, because this is kind of a decision point right here. If you want to feel more confident about that, you could look at those two time series because they really dominate this drainage area. And if you plotted them, did some statistics on, well, what's annual average volume or depth? What's the typical storm size? And if you felt you're pretty good about that, those were similar, then using one versus the other really won't make much of a difference in terms of runoff in the model. So that's generally what we recommend as well. If you're split even like this, you can look at the time series and say, all right, well, these are more or less the same. We can just pick one and apply it everywhere. And it really is not going to impact model results very much. If that's not the case, and they are actually pretty different, you can blend these two in a composite average weighted depth and create it as one. You'll rename it something else, and then you can feed that into LSPC. John, any thoughts on adding to that?
Yeah, and those are all great ways to manage cases like this. I would add that when you're selecting time series, as much as possible, try to keep one unique set per drainage area that you're modeling. The reason being, like in this case, if you were having these two main gauges and you were trying to blend them together, if you did an area weighting just straight against the hourly time series, you could have a scenario where maybe the peak of the storm was at 1 o'clock and the peak was at 2 o'clock in the other file, and you smash those together and you get two that are half the size. Even though it's the same amount of rainfall, the intensity is a key parameter because of the process-based simulation. So you could get sometimes an order of magnitude difference in the predicted sediment just because the peak was diluted, if you will. So that's just one consideration there. There are more sophisticated ways to do the area weighting. You could area weight them on a longer time and then disaggregate them to hourly. That's another way to kind of protect yourself against that sort of thing. But in most cases, you can pick the one that has the highest coverage over the watershed, especially since the area is not that big, and run with that.
Yeah, I would agree. I don't want to talk too much about this because it's an important point, but it's also not something that I don't think people should worry too much about. I think 99 out of 100 cases, you're just going to pick the biggest coverage or the most coverage in your drainage area. So in this case, it would be, to me, I see green as the biggest. And then you can just kind of move forward and put your energy towards other aspects of model development.
Yeah.
The next part, once we have that meteorological zone figured out that we're going to apply P391C_3 to our drainage area, the next question is, all right, well, what's the time series? What's the condition that we're going to be using? Is it a 10-year time series, the 85th percentile storm, bacteria storm, average or 90th percentile year? We have all that data again on the WIMS webpage in the repository, and this is again the link here. It's within this LSPC panel. About halfway down on the page, there is all this data that can be downloaded. And this is the precipitation for all these different conditions for all of LA County within the WIMS model domain. And so all that data is right at your fingertips. You can get right in there and look at those precipitation time series. So once we have all those pieces together, the next part is to download LSPC map. This is an interface that we developed last year as part of the WIMS 2.0 update, which really helps expedite and streamline the process of running LSPC. And so John and I are going to pause in a few slides to actually show you how to open up, configure, set up LSPC so that it will give you output that you can use in Sustain. And so that's coming. But before then, this is the location on the repository where you can download that model package, which includes a number of things. It includes the executable itself, so that then you double click on your desktop or within your folder that pops open the application. It also includes the weather time series that we developed, which is the same as this right here. There is a Microsoft update in there. I think there's actually two, because Microsoft just updates things through time. We've included two of those that need to be updated, or two aspects of the operating system that need to be updated so that you can run LSPC map. And so those two things, as well as the map, LSPC map as a program, I imagine you'll need some sort of administrative privileges on your computer. And so when you do get into this point in downloading LSPC map, I imagine you'll have to reach out to your IT department and say, hey, I'm going to download this this package of data, and there'll be some installations, and you'll need their help for that, or you'll need them to kind of check off that that's okay. What we're not going to get into too much is how to install it and how to configure it from kind of zero, or from kind of this baseline area. But we do have an installation document that goes through that, and that's a part of that data package on the repository. And so that'll say, this is how you download it, unzip it. There's what's called the MSI, which is an installer that helps you walk through how to put it on your machine and get it ready for simulation. And so all those details are there, and it should be able to help you through being able to install LSPC map. So with that being said, this is a little bit of what it looks like. And once LSPC map is installed, you'll be able to select your sub-watershed or multiple sub-watersheds of interest and run the model for the purposes of getting output for Sustain. And so that's what we're going to get into now. Actually, I guess before we do that, the output that you're getting for Sustain is what's called the unit area time series. And it is a runoff time series for each HRU within that drainage area. And this is runoff and pollutant load. And I don't think we'll get into describing this too much just yet. I want to get through LSPC as a whole first. And then as we start to get into what Sustain needs as input, we'll get into more depth about what this is. But just showing it as kind of a preview, the output you'll be getting is going to be this text file type output. That's just a time series that you gave the model precipitation, and LSPC as a model will give you out runoff and pollutant loading that resulted from that precipitation in your watershed. So with that, John, I believe you're co-host, and you can share your screen. So I'm going to do a stop share on mine.
All right, I'll go ahead and share screen one. Okay, so can you all see LSPC map?
Yeah, looking
awesome.
Good.
Okay, so this is LSPC map, and once I've installed it and set it up on my computer, I would go to, I could create the desktop app, or through the installation, you can access it this way. You pop that open, and it opens up LSPC map. Once we're here, I'll just briefly look at the configuration just to give you a view of what's happening there behind the scenes. I have a location where I've installed the model. I'm pointing this interface to a shapefile, because the shapefile is going to be what we use to interact with the actual model data. We have the field in the shapefile that has the attribute of the subwatershed number. And that's the key translator between the spatial view here and then the actual numerical data behind it in the model. The database itself is also linked dynamically here. So we have selected a project that we're going to simulate, and we've identified which subwatershed in our system has that rainfall data that we were looking at before that is most representative of our system. And so all we need to do is run that one single subwatershed. And it just so happens to be subwatershed 6121. That's the one that has the time series. And what I'm going to generate in this example is the unit area time series. You'll see there are 99 files in this folder. Each of these is one of the hydrologic response units in the model. So the first set, the 1000 series through 10,000, these are the impervious HRUs. Those are the hydrologic response units. And then the pervious HRUs are here. Now, the model, when it's generating these unit area time series, each of these files is going to be, and Ryan touched on this with that in the view there just previously, but just to give you a sense of what it's going to look like, it's got the information for 1 acre of this specific HRU. So we're looking at road, freeway. Now, it doesn't necessarily mean that this HRU exists within that subcatchment, but what this is doing is it's generating for us a time series for what one acre of that HRU would have produced in terms of flow and pollutant loading. That's what's represented in here, and it's on an hourly basis. That becomes the boundary condition into sustain. When I get to sustain, I have the opportunity to say, okay, I have 5 acres of this HRU, 10 acres of this HRU. Essentially, I can reconstitute what is in the drainage area for my BMPs. This is a huge advantage because when we're putting the BMPs into the subwatershed, it's not just running all the HRUs in the subwatershed as they are. We might have a network. We might have intermediate places where we're sending certain HRUs, and then the outflow from those BMPs are going to go down to another one and so on. So this unit area translation is pretty powerful. It gives us an opportunity to kind of reconstitute, recook our subwatersheds the way that we need them to hydrologically represent the flow pathways. So,
John, sorry, I don't mean to interrupt you, but we have, I think we have maybe we can spend 20, maybe even 30 minutes on LSPC map as a whole. So like the unit area time series, if you wanted to pull that up again, that text file, to me, when I first started, that was a really overwhelming thing to look at. And so I don't think we talked about these columns and what they represent, and the time aspect of it. So I think we can get a little detailed here and say, all right, what is Suro? What is Agwo? What are these different columns? If I want to, for someone who's never seen this before, it just looks like a jumble of zeros and ones and dates. And I think we can really use this as a resource so that someone who's like, wait, what the heck is this text file? You can just, if you have someone that you're training up, you can just kind of show them this part of the video. And then I think this will speed them up to that.
Awesome, that's a great point, and thank you for that. The Suro that you're seeing in here, first of all, the structure of this file, the header information tells us the order of the columns that we're seeing in here. So we have 1, 2, 3, 4, 5, 6, 7, 8, and 9 columns of data. Suro is surface runoff, and it's inch acres per hour, which somehow coincidentally is very close to a CFS if you do the unit conversion. But then the second column is AgWe, This column is here. It's not going to be used in the context of this run, but it is an output that was done as part of the sustain, because typically for an HRU, you might have not only the surface runoff, but you might have some of the water that is going into the ground, and you might need to track that for some reason in sustain. But for now, we're just dealing with the surface runoff that's going into the BMPs. The other columns in here, we have our total sediment load, SO-SED, and then each of the water quality constituents, nitrogen, phosphorus, cadmium, copper, lead, and zinc, as the SO equal 1 through 6. So the columns in here, the first ID is the HRU ID itself. So we're looking at 1000. This is the HRU ID for road freeway. The second column is our year, month, day, hour, minute. And then we start with surface runoff, AGWI, SO-SED, and so on. So that's the structure of this. And all these are generated for 1 acre of each HRU, of which I have, well, there are 99 files in this folder. There are 2 additional files in this folder, AGWO and IFWO. Now, they're not going to be used in this application, but when you simulate a subwatershed 6121, this represents the full set of information to generate all that's coming off the land surface. The AGWO and the IFWO represent the total base flow, interflow, and active groundwater outflow for that, from that one subwatershed. It's aggregated across all the HRUs that were in that subwatershed. So in some cases, when you're running a larger network in sustain, and you need to maybe route your base flow through the network to some downstream point where you might divert some of that flow into a BMP or a regional facility or so on, that's the piece that you would have to be able to link that in. We're just dealing with runoff in this example, but this just gives you a view of what is in this folder. Now, what we're going to do in this exercise is how to generate these files from the LSPC map. Pardon me. All right, and so here is our view of our subwatershed. I've kind of pre-cooked a scenario in here, and you know the way that this interface works, it allows you to go in and select a single subwatershed, or you can go and select a whole network of subwatersheds when you click this upstream. If I click on a specific point in the network, the model will select the upstream network. All the subwatersheds that are hydrologically connected to that will be selected. In this case, what I'm going to do is just select my East LA Median Project subwatershed. I've defined that as a scenario. So I went in beforehand, selected that subwatershed, and then saved it as a scenario. And so likewise, you know, I have all other scenarios that I've defined. This is the one for the whole LA River. This is Malibu. And here's my itty-bitty project for this case study. So we can just zoom in to see what it looks like. So kind of a nice feature of this LSPC map interface, it's actually a browser emulator. And so it's actually looking at aerial imagery from OpenStreetMaps and right off the web. So it's as if you're working in a Google environment, if you will. And here's our subwatershed model boundary. I can see an aerial photograph underneath it to make sure that I am in the right place. It's not exactly the same shape as the one Ryan was showing before, because that was the drainage area for the specific project. This is the sub-catchment in the model. So we will be doing a different boundary in sustain than in LSPC. But ultimately, we're trying to get the unit area runoff, which is based on the rainfall that was associated with this one subwatershed. So we're okay, because that is not going to change. That's independent of the drainage area. So once I've selected my East LA Median project, I can tell LSPC that I want to run this project. Now, by default, your tool is going to come in the default setting where it's just going to run this sub-watershed and give you an output. For this application, we don't want that. We want to use an advanced opportunity because we're going to tell LSPC to do something slightly different. So when I press run this time, of course, it's going to open it up on the second monitor over here. When I press run this time, it brings this screen up. I press OK. I don't need to change any of those settings. Right.
Real quick, John, if let's say, is there ever going to be a situation where a user, like someone at County Public Works, would be interested in changing or adjusting those, or should it always be sort of a rubber stamp on that page?
That particular one, I wouldn't change it, because if you're changing it, then you're deviating from how it was calibrated. The only exception is if you were to go in and recalibrate the model and use monthly variable parameters for all of your hydrology terms and do a lot more than what was done as the default. Well, then in that case, you know, even in that case, if you had already done that in the database, it would already come up with whatever you configured at that time. So even then you wouldn't need to change it. Only time you want to change that is if you're trying to kind of start that process towards redefining the way the model is parameterized.
Okay, perfect.
All right, so what you're not seeing happening on my other screen is it's loading. Once it's finished loading, I'll bring the interface, okay, down so that we can see it. So what happened is it went and it grabbed sub-watershed. I'm just going to go look at the stream network for this. Sub-watershed 6121. Now, on this card, I clicked on this card because there's a output control. This is a really important thing that you have to make sure you turn on. Otherwise, your model is not going to generate any output. Part of the reason why this is off is because in the calibration baseline, we turned it on for the places where we had a reason to look at output for comparison against observed data. So this wasn't one of the calibration sub-watersheds, so it was off by default, so it just doesn't fill up your hard drive with a bunch of unnecessary files. But in this case, we want this on because we want to generate unit area time series for this sub-watershed. Now, the other thing that I want to look at here is the time period. Now, the time series that were read in were the default time series. So this is the long-term simulation time series. The time period that I'm interested in, I'll just generate one that looks exactly like this file. So it's from January 1st, 1990 through May 17th, 2020. You know, if that's what I want to do. One way to do that is this knows the boundaries of those files. So I just set the start time to be the very beginning. All I'm doing is I'm pressing the end. Okay, if I want to change this to be this was May 17th. Okay, it looks like I don't have the latest time series. Well, I'm going to generate this through 2018, through water year 2018, just for example here. So we'll go to the end of water year 2018, just for example. Now, there's a simulation period and an output period. The reason why the model has them is so that we can throw out a period of time as a spin-up period if we don't want to include that in our boundary conditions. So let's say this is from January 1st, 1990, but let's say I wanted to just run the water year starting in 1990, October 1st. I start it from January 1st so that the first 9 months I can just ignore. And then the output is going to begin on October 1st, 1990. So the other thing that I want to do is to make sure that I put this at hourly or time step, doesn't matter, because the time step of the weather data is hourly. So both of these are going to give me the same result. But just for kicks, I'll use time step for this. These are very important steps in the process when you're doing this, because otherwise you're going to generate unit area time series that are daily, which you can, but it's not really what you want to load into sustain. You want to put in there the full texture of the hourly time series.
John,
Right.
I had a quick question or comment about, the difference between input control and output control. And is this what I've heard it called model spin up before, which is where, if I'm interested in a particular water year, I don't start the simulation on day one of that water year that I'm interested in. I let the model spin up a little bit. If there's reservoirs, we may want them to fill up a little bit. We may want, some sort of existing condition in terms of soil moisture or something like that. Is this how that's controlled?
That's exactly right. This is how you set your spin up period. And so in this case, we've defined a spin up period of 9 months that we're going to disregard. Another key thing with this output period, this is what is going to drive your summary file. So the model allows you to generate summary files for land use, stream, point source, average annual basis, yearly or monthly. Those summary files, we're not going to get into that here, but they're pretty important. They're pretty a handy way of summarizing a lot of detailed information out of the model into one nice CSV long form file. So what I'm trying to do here is to generate my unit area land use time series for sustain. So I want to make sure that this box is checked. And just because we're customizing everything, I'm going to go ahead and redirect this to the same folder where I'm going to have my sustain output files. So it's going to go to the model. Wait, let me make sure that is. I need to go to my current input folder. LSPC data, and I'm not going to overwrite this one. I'm going to just make it, I'm going to create a new folder. Now, if you're just creating one new folder, it allows you to specify one new folder that doesn't exist. It'll generate it, but you can't specify a whole path of new folders that doesn't exist. Just gives you one. So all these before this point have to be there. So I'm going to put everything into this test folder. Now at this point, I think I've checked all the boxes. I've gone to make sure that in my stream, just to recap, in my stream network folder, I've selected output control of 1, meaning that I want to generate output for this subcatchment. I've gone into my temporal settings, added my spin up period that I want to throw out, and then started the model from the period that I want to evaluate. That's done here. And then finally, I've gone in and selected that I want unit area time series, and I've specified my output folder. At this point, this instance was spawned off of the interface for the selected subwatershed that I want. If I want to commit these into a file that I can come back to later, it's usually really advisable to do that. I'm going to go ahead and save this in the same folder. This is my test run for 6121 input file. So now I've committed this request into an input file. I can always go back, come to it and run it or change it, do whatever I want from there. All right, now at this point, we are ready to run. So fingers crossed, we press the run button and oh, well, I guess even though it was one sub watershed, it's quite a lot of information. It's a long period of time. And so it is running and generating this file. We have a pre-cooked version of those outputs here. So we can continue from there. At this point, if it might be good to just ask if there are any questions about this part of the process. How are we doing on time, Ryan? Do we have time to look at this input file or? Yeah, okay.
Sorry, I was muted. Yeah, we do.
Okay.
Definitely.
All right, so this is the input file that I saved. And so just to give you some feeling of what is in here, at the top card is divided into these, we call them the cards, going back to the old-fashioned computing days where each card had a set of rules. This is card 0. This has the general controls. So this tells me that, and it's the order of the controls are mentioned here. We're not simulating snowfall. That would be a bad day in LA. We're simulating water, sediment, and we're also simulating general water quality constituents. We're not simulating any of these other ones. So that's what this card is. And then here is the next card. Here it tells us, this looks familiar. This is the preset file for this subwatershed. And so it tells us that for this subwatershed, we're using this precipitation time series and then this evapotranspiration time series. This is how those files are combined together to represent this weather station 668. Weather station 668 represents a combination of this precip and then this ET. And so on. Here's my output folder where I specified the inputs are here. My output folder is here. It's created this folder and it's running it. And then at the same time, it tells me that I had 96 possible HRUs. If I go down to here's where I specified my simulation time period. If I go down to card 90, card 90 has my land use information. So for this subwatershed, for this HRU, I had this much area in acres for this subwatershed. So if I was running the I am running the subwatershed, it's going to give me runoff aggregated for all the HRUs in this watershed, and it's going to give me my unit area loads. Notice that we didn't have some of these HRUs, like there was no irrigated A soils, low slope over an unconfined aquifer. There is none of that in this subwatershed. But my unit area time series will have a file for that, just because it is a possibility. Part of the beauty of this later on is, imagine if you're running and sustained and you want to do land use change scenarios. Let's say you want to increase development in your drainage area by 10%. That gives you a chance to kind of reconstitute by adding a little bit more impervious area, reducing your impervious area. I mean, if that's what development is doing, assuming that that's what development is doing, you can reconstitute your footprint of HRUs to represent a land use change scenario. And so that just is an illustration of some of the flexibility that comes along with that.
John, I'll add on here that, as we go through this, and I don't know how much we need to go through the input file, but the idea is that, I don't think Public Works as users will probably go through the input file. Hopefully, won't have to go through this. So if this seems a little overwhelming and daunting, it's because there's a lot of information in here, and we built well, LSPC has been built and has that sort of dialog box interface, and LSPC map has been built so that a user can kind of stay out of that realm as much as possible and work on the interface. One, because that's a little easier and I think more intuitive than a text file. But I think what John wanted to show is that, the decisions that is being made up here on the interface, that does get plugged into an input file. And that's what LSPC executable reads and does this work, or how it knows the boundaries of this work that it's going to do on the subwatershed. So don't feel like you need to know all the details of those cards in the input file. I don't know if I would envision a scenario where any of you all would have to dig into that and make any adjustments there.
Yeah. And then also, I mean, this example, I ran it and I generated almost the entire time series. Typically, when you're running this, you could be doing a design storm. A design storm will just take a couple seconds to run. I mean, we started from 1990. We've gone almost 10 years now, and we're about a third of the way through the simulation. So that's about right. If you're running that kind of time period, that's what you'd expect. Oftentimes, selecting that critical period is an analysis that you do before you come to the model. You can look at, or you can use the model to look at stats of your entire, let's say your assessment point is the mouth of Rio Hondo, for example. You can go to the Rio Hondo time series and then look at, when did we have really wet years, when did we have really dry years, and then from that, pick a year that you want to use as your representative year for your analysis and say, okay, I'm going to run just water year 2017. And then you go and use that to select your period. But yeah, those kind of judgments, those kind of decisions do involve a little bit of analysis beforehand. This is just running the entire set, so it's there. But this is going to continue. We already do have the pre-cooked set of outputs that Ryan, you can work from. So at this point, I think I can stop sharing and turn it back to you if you like.
Yeah, I think that sounds great. All right, so I'm going to go back over to my screen, and I just want to bring home the point about what you're going to get on the output from LSPC. So I'm actually I already have that LSPC output kind of pre-baked. It's in this folder structure over here, and if you'll recognize these output folders. And if I go to long-term, again, this just shows for all 96 of the HRUs, there's a text file. And if I open up road freeway, I get that time series again. To me, I actually don't run LSPC very, very often. I usually have someone else run it for me, and then they give me this, and I'm like, okay, great, thank you for this. And I just trust that it's right. But there is probably some level of QA that I would, generally recommend that anyone does when they're running the model. If you want to feel confident and comfortable that the model is giving you sensible output, this is the text file to do that, or this is a place to do that. And for me, text files are not intuitive to work out of. So what I would do if I wanted to kind of on the fly just take a look at what this output is, and it might be a little bit to paste. So let's see if I can just do a portion of it and put it in here. So I can drop this into Excel really easily and neatly, and I can see all those tab delimiters, they just drop into the cell. And so if I wanted to plot this up and just see what that hydrograph looks like, because that's what this is a hydrograph, I can see a little bit of that coming through here. And I'm only doing the first couple days, and apparently there wasn't much activity in terms of precipitation, so there isn't much of much action happening here. But to me, this is a really useful way of saying, all right, well, you gave me a bunch of data and runoff. What does that mean? What do I do with that? How do I think about that? To me, it's as easy as let's just put that into Excel. To me, that's something really familiar and easy to work with. and I can make plots. I can look at average annual summaries. The format for this text file is a little, I don't know, not really my conventional way of looking at text files. So you can actually aggregate the year, the month, the day, and the hour into a single cell. I forget how to do it. I think you can do something like year, and you're like, hey, yeah, this is a year, and then you can do month. Yeah, hey, this is a month over here, and you can aggregate that and bring that all into one column here. And then if you plot that, you can get a really good picture of at every hour of every day of every year, this is the runoff that was generated. And then
I'll just plug in on that, Ryan. That would be the date function.
Date function. Thank you.
Yeah. So with the date function, then you say date and then year.
Yeah, there it is.
On the day. Yeah.
Beautiful. Now it's all in one. And sometimes what I'll even do is I'll use this function. What is that doing right now? I was having a tough time, but you can transpose the selected cells, and you can just put them over here. So instead of going counting over here and then counting over there, you can just set those, blow all these out, and you can see exactly what's over top of each of these. And to me, there's a little bit of work involved to kind of get this set up, but once you have it set up, you can actually take, another input file, output time series, and you can just paste the bulk of the time series right here. And you don't necessarily need to update this other stuff because every input file follows the same format. So that's how I kind of look at things, just to get a feel for what's going on and making sure things are looking right. Because sometimes I'll run a sustain model and the output looks wrong, and something is off. And I don't know if it's this. I don't know if my BMP isn't characterized correctly. There's a dozen or more things that can go wrong. And so I'm being able to kind of like check this and say, you know what, this looks okay. Nothing's weird here. There isn't, this 100 acre feet of water coming off roadways for some reason that doesn't make sense. So I've kind of checked that box here. Or if runoff is really low, like if this is 0 all the way down for 10 years, then I know something's wrong there too. That's not quite right. So that's a little
bit. Just to recap on that, this file is for 1 acre of runoff. So that's another consideration. You're going to actually reconstitute the drainage to your BMP in sustain by saying how many acres of this file exist.
Yeah, that's a really good point. And so when I look at these, I'm always like, wow, those numbers are so small. But what John just said is that this is a representative acre of roadway. And so in our drainage area for this BMP, there may be 30 acres of this type of roadway or HRU, and 20 of another one, and 10 of another. And so that's a multiplication factor on this this time series. And so what sustain does, it'll load up all of these HRUs, and then whatever acreage we specify, it'll multiply that number times all of these, and then it'll aggregate based on drainage area. Like if there's, what I was thinking in my head was, if this was rooftop, and we do have a rooftop one, don't we? Let's say Elon Musk gives you a call. He's like, hey, I've got this Amazon warehouse. It's going to be huge. We need a cistern to capture that. You don't need 96, actually. You don't need 96 HRUs to do that. You just need roof. And whatever Elon Musk says is the acreage of that, you put that in that sustain file, and maybe it's 100 acres. And sustain is just going to take these numbers and multiply it by 100. And so there's not any sort of like weird math, or there's nothing too fancy or complicated. We use the unit acre because it's a small enough standard that we can apply and scale up to any size to meet the drainage area that's there. And so if it's 100 acres of this, or 10 of that, and 12 of that, and 11 of that, sustain does all that work to aggregate and multiply all that. We just have to give it an outlet at the end and say all of that HRU and runoff that results from that, it goes to this point. And that point might be a BMP, it might be a node, it might be the outfall. And so that's what the sustain part of it is figuring out that drainage. What we're doing here is just giving sustain those pieces, those unit area pieces of runoff and pollutant loading, so that it can run any sort of kind of combination of HRUs that we want to give it. Whew, that was a lot. John, I'm going to wrap up this section. Is there anything else you think we should add or is worth kind of mentioning here as we wind down on LSPC?
I think that covers it.
Okay.
Right, the good transition to sustain.
Great. So that was really the end of our first exercise, and what we hoped you all got out of it was, I'll do a brief recap here, which is we want to get the data that we need in terms of the drainage area, meteorological zones, the condition we want to consider, downloading and installing LSPC map. John walked us through that we want to do the advanced function once we've selected our subwatershed of interest. We click through that first screen, we make a couple changes in terms of output and dates, and then that final checkbox on the unit area time series output, which is we were just looking at over here, that guy. And then once we've kind of looked at those files after running it, look at those files, feel good about it, feel confident about our LSPC results, then we're ready to transition to sustain. And so that's what the next exercise is. But because this is such a long string of slides, we're going to do a quick break so that people can get water, digest a little bit of everything that they heard, go to the bathroom as needed. But we want to keep it pretty short so that we can kind of keep momentum going. So I have on my clock 9:16. Let's pick up again at 9:21. So for the next 5 minutes, do whatever you need to do to get yourself mentally prepared for the next, the next set of slides, and we'll pick up then. See you all in 5 minutes. Okay, it is 9:22. I'm gonna jump back into things. I was hoping to see the participants just so I can keep a handle on raised hands and that sort of thing. But to keep us going, I'm gonna jump right back into the slides. We actually have a little bit more left to exercise 1. So what we just finished was the LSPC portion of it. Now we're going to get into a little bit the back half of exercise 1, which I don't think will take too much time. So getting back to kind of that framework of what I was thinking earlier in terms of, if Steve or John comes up to me and says, hey, I have this project, I need you to run sustain for. We've gone through the LSPC part of it. We've generated that HRU runoff time series. The next part is to figure out which HRUs are in our drainage area. So John was showing how we can generate time series for all 96, but we may not have all 96, and we don't necessarily know how much acreage of each is in our particular drainage area of interest for this project. So again, I'm showing this map of where we are in terms of our project drainage area, and we're going to want to go grab data from the from the WIMS web platform that we have. Again, the link is up here on the top, and we want what's called the complete HRU raster. There's 2 here. There's the mapped HRU raster, complete HRU raster. Again, this is one of those things where we have both so that people can use either. Mapped doesn't include a number of things that the complete one does, and we don't really need to get into those details, but you'll, I think, always want to use the complete HRU raster. It includes disconnected impervious area. It includes irrigation and overspray. It is the complete set of HRU raster, or the set of HRUs for WIMS 2.0. So this is what you would download, and what that is a TIFF file or a raster of the model domain. And so it has, I don't have a legend here because there's 96 of them, and it would get pretty cumbersome pretty quickly, but it shows, what is high slope, tall vegetation, soil type A, or low slope, soil type D, impervious cover for a rooftop. It has that whole range within this. And what we need to do is figure out, well, what's our composition for our drainage area? It's great that we have this whole area, but we only need the portion for this particular model area. And so what you'll do whenever you start a new project is start here at the full scale of HRUs, and then you can always clip down to your drainage area of interest, which is what I'm going to walk through pretty quickly, because I think I imagine most people are pretty familiar with how to use some of these clip processes from ArcGIS. But real quickly, I'll just go through how that works. So once you've opened up an ArcMap work session, you can use the clip raster function to take that big HRU raster and clip it down to our drainage area of interest for this particular project. So that's what we're showing here. The input raster is that complete HRU TIFF. The DD merged is the drainage area shapefile. I've checked these two things to maintain my clipping extent. I've selected a place on my desktop to output that resulting clipped raster. I also make a couple adjustments to the environment section here. So I'm not sure if other folks do this, but this is what I do, especially when I'm taking two different data sets from two different places. I need for them to be in the same coordinate system, just to make sure everything lines up one-to-one. So that's what I'm doing here, is that in environment settings, you can set the coordinate system to any coordinate system that you want. The state plane 5 is what I pretty much always use for everything in this part of California, and LA in particular. And so that's what I've done here. I've this layer, my drainage area uses this, and so does the HRU raster, but I'm doing just kind of a double check here to confirm that everything's in the same coordinate system, because that will, or rather the same projection, because that can make your results goofy if you don't have that quite right. The second thing is to make sure that the resulting clip that we're creating is at the same cell size as the raster, the original raster that we're using, and that is 6.56168 feet, which seems like a random number, but that's actually 2 meters. And so the cell size, or the pixel size, for the raster for this WIMS HRU raster is 2 meter by 2 meter. And so if that's the size that we're using to kind of cut along this drainage area, that's the output size that we want for the pixel. So again, that helps it to be one-to-one, and we're accounting for all of that area within our drainage area. And so once I've done that, I've clicked OK, I've hit execute. It might take a few minutes depending on how big your area is, but this is what results. That big drainage area that we had before, or not drainage area, but that big raster that we had before, that has been clipped down just to our project area, because this is the area of interest for us. You oftentimes have to build a raster table for these after these clips, and so there's another function in ArcMap that will do that as well. And so it's really easy. I just do a control search function within ArcMap for build raster table. I drop in that new clipped HRU raster that I have. I check overwrite just in case, and what I get is an output table. And there's a couple things that are worth mentioning here, and that is that the values here, those are the HRU codes. And so we showed 1,000, 2,000, 3,000 in terms of our, let's see if I can pull it up again over here, in terms of our HRUs that are coming out of LSPC and into sustain. You'll notice that these numbers here will match exactly with the numbers we have here. And so I've got 22,000 cells of road and freeway, 47,000 cells of road primary, and so on and so forth. What's really important here is that count is the count of cells, or it's the count of the number of pixels. And if every pixel is 4 square meters, that's the resolution of the original raster and the raster that we created. There's some math that someone would have to do to say, all right, well, 22,432 cells equals some amount of acreage, which is the unit that Sustain expects in the model. So there is an additional kind of bit of math here that someone would have to do. So you got to find that conversion factor for, well, what's 4 meters? How many meters are in an acre? And then you can use that to convert to get acreage of acreage of each of these HRUs. So that's kind of a quick, simple rundown of it. There's more complicated ways to do it. We do have a utility tutorial document that goes through everything that I just explained pretty well, but also if you have multiple drainage areas for multiple different BMP types, there's another avenue in GIS that you would take to do that, and that's zonal histogram. We're not doing that here because we're doing a pretty simple drainage area for this particular project. But in the future, if that comes up for you running a model, I would recommend going to this documentation and looking at how that describes that process, because that'll be helpful in showing that pathway forward.
Yeah, just one comment on that, Ryan. I think one key thing behind this complete raster, and Ryan touched on it, it has baked into it a lot of the key assumptions that went into the model build. So when you look at this, we talked about directly connected impervious area. In the model, the mapped impervious area is what you see from a bird's eye view. But in the model, the actual response, let's say you have an acre of rooftop, but then it's surrounded by a 10-acre lot of grass. The amount of the effective impervious area, some of that runoff is going to go over the pervious area. That whole response is going to be very different than an acre of rooftop surrounded by a quarter of an acre of grass, right? And so the model uses directly connected impervious area to kind of adjust for that. All those assumptions are baked into the complete raster, because we've gone in, done that empirical relationship to translate direct mapped impervious to directly connected impervious. Other assumptions like the irrigation, which is represented as a portion of the pervious area. And then even within that, irrigation overspray, which is a percentage of the impervious area that's adjacent to pervious land that could potentially receive overspray from irrigation. I mean, imagine trying to account for all of that. Those things aren't really spatially represented traditionally in the model, but in this raster they are, because what has happened is we've taken the percentages from the model and then sort of peppered on those impacts into the raster. So for that rooftop example, the directly connected impervious area, what you'll see is if you zoom into that rooftop, you'll see some peppering of perviousness on top of it. You wouldn't want to live in that house, with holes in its roof. But as far as the model is concerned, it's represented how much of that imperviousness is effectively connected. And so you don't have to do those translations if you use the complete layer. Likewise with irrigation overspray, there's some peppering of impervious overspray area on the pervious area to represent that, you have some of that area as overspray from irrigation activity. All that is explicitly baked into the complete raster.
Thank you, John. That's a great point. So to, I guess, summarize it, all of those complexities that we've built into the calibration of the model that's baked into the HRU raster, that's already in the complete raster. And so if you want kind of the easy button, you just select this and you download it, and it's already taken into account. And so you don't have to think about those things. We've already done it for you. So that's that. So So once we have the, let me go back just a little bit here. Once we have all of the HRU and the area set up, in my mind, the next part of the project is, all right, well, I've got LSPC done. I've got the HRU acreage understood for the drainage area of my project. The next thing is, well, when that runoff from that HRU area gets to my BMP, what does that BMP look like? Is it a bioretention cell? Is it an infiltration well? And what we want to do with this section is to start to get you all to think like sustain. So if you can think of the processes that sustain is doing and how they will impact a BMP, that's kind of what these next set of slides is. And so when someone is going to give me a project for a particular area and they start talking about the BMP, I start to think about it in terms of these segments. What is ponding height? The space on top of the BMP, if it's a cistern, that's like the 5 or 6 feet for that cistern. Is there soil media? What's the depth of it? What's the porosity? That helps understand the amount of storage in there. Infiltration rate, how quickly does water percolate through that media? Is there or isn't there an underdrain? Is it lined? What type of treatment exists in that underdrain? Is it a percent reduction? Is it a constant, or is it a minimum effluent concentration? Is there an infiltration rate for the native soils? If so, what is it? And so taking that kind of picture that we had before and starting to break it down by slice and showing that each of these sustain kind of handles these things, at least in terms of parameters, with different values in different places. And then we put it all together in the model and say, hey, this is our BMP as a unit. And then it will behave accordingly. And so infiltration well, that's the type of BMP that we're going to be using in this project, in this exercise. And so let's kind of turn our attention to that. What does the ponding height, soil media under drain, and native soil look like for that? We have to think about it in terms of consistent layering. So it's kind of like, I don't know, like a parfait or a cake, a layer cake, where it's, the ponding height is a certain height from A to B, and it is only in that section from A to B. And so what makes infiltration wells a little funny is that you've got ponding in the center here, but you also have media around it. Sustain can't model the compartments of the BMP in those terms. So what it has to do is, it has to put ponding on top, and that media, that volume that's being, the volume available for stormwater, we put that below it. And so instead of having this vertically segmented BMP, we have to kind of reimagine it in our brain. We have to think like sustain, so that we can understand, or we can characterize the storage capabilities of that unit as it exists in reality, but we have to reimagine it so that sustain can use that information, or can have those volume and have those properties so that it would be simulated as it is in the ground, or how it would be in the ground. And so for this particular project, there's a big ponding height. We went ahead and pulled the Safe Clean Water application for this project to get an understanding of, well, what is the ponding? What is the soil media, if there is any? And so what that information is here is, we have an acre of BMP footprint, which is really important because that is your, the bigger that area is, the more infiltration you can have happening in 1 hour in the model time series. And so we got a big footprint, 1 acre. We have really tall ponding, 22 feet. So that's 22 acre feet. To me, this is an aggregation of multiple dry wells. I don't imagine that there's one dry well that looks like this. It's probably, I don't know, 50, 20, something in that range. And all those are being pulled into one unit to kind of simplify the modeling process. And there's also the infiltration rate of 4.63 inches per hour. So this is, in that bottom left corner, is actually all we need to simulate this BMP. There's some other knobs and dials that we can change and adjust, But this is the kind of the minimalist amount of things that we need to work with. And this infiltration rate is I should say, is the native soil infiltration rate. It's not soil media. There actually isn't any soil media as specified in that safe clean water application that we pulled from. So we're not representing soil media here. It's just ponding, and whatever stormwater is occupying that ponding space, it will infiltrate at 4.63 inches per hour. The other thing that I mentioned here was that there is a decision point a modeler can take in terms of how to represent multiple BMPs. As we're doing it here for this example, we're taking maybe 20, maybe 50, maybe more BMPs that would be implemented separately, and we're just smooshing them all together. And for the most part, that's fine. They are all duplicates of each other, I imagine, even if some of them were a little bit different. As long as that stormwater volume is there, and as long as that infiltration surface is there and is accurate to what's actually happening in place, then you've essentially captured what you need to in terms of representing that BMP as a lumped unit. You have the option of multiplying them out individually. It does take a lot more work to characterize each one of those. And you have to control drainage areas to each one and routing between BMPs if there are any. But in this lumped approach, you're probably going to get pretty similar results, and it's going to be a lot easier to build a model that looks like that. And so that was the decision made here, is to keep it fairly simple, aggregate all these BMPs into one type in the model, make sure that the ponding, the volume, infiltration surface area, which is 1 acre, the footprint, that those are all consistent with all those BMPs added up together. What we don't want to do is add, all the volume, that we have the right volume in ponding, but we don't have the right surface area. Maybe we have a small surface area, and so the infiltration happening will be sort of constrained in that way. And so that's one thing you want to watch out for. If you do start to bring these things in together, you have to make sure that the aggregated BMP performance is similar to what it would be if it was disaggregated. John, any thoughts you want to add on to that?
Yeah, I think this is all great, and also just thinking about the different types of BMPs. There are certain ones where you want all of the water from the drainage area to come into the BMP, mix, and then overflow. And there are certain other practices like the green streets or curbsides, where if there's a curb cut, the water that's flowing in will go in until the BMP is full, and then no additional water will come in, it'll just bypass. And so that's probably downstream in the process still to be discussed. But as you think about the configuration of these, those are two key options, because it makes a difference. When you're talking about regional facilities, wet ponds, all the water comes in and then overflows. You're going to get a different water quality response than if you're doing a bioretention with a curb cut, because that will have the water coming in, fill up. Once it's full, the new water will bypass. Think first flush, right? In that case, you're going to have a first flush response where you capture it, and then all the additional water beyond that is relatively clean. So that adds to dilution downstream by letting that water go. That's going to have a big impact on your simulated performance, whether you mix it or you let some bypass once it's full.
John, that's a great point. There is two things I want to say. First is that there's a specific knob that adjusts that in the input file, and we're going to show you exactly where that is. And so if that sounds like kind of complicated and hard to wait, you're right. How do we do that? What do we do? Well, there's just one switch you change in the model. And once you've done it, you've accounted for all those complexities that John's describing. The second thing, in terms of when we kind of aggregate these BMPs together to represent them as one, in the example we have here, we're taking 20 or 50 or so infiltration wells, and we're pushing them all together into one. And we were saying that that's probably just fine for simplicity's sake. for the sake of simplicity. But I think when it gets a little more complicated, if we have a project where we're doing 20 dry wells, a couple bioretention cells, a cistern over here, a filtration unit on the back end of a property, well, now it's starting to get pretty different. Like the cisterns are going to behave differently than the infiltration wells, which will be different than the bioretention cell. So as you have different types of BMPs coming online, those would be represented individually. And so if you have 3 bioretention cells, you can probably smush those into 1 representative bioretention cell. And if you have 10 infiltration wells, you can smush all those 10 into B1. And so in that case, you have 2 BMPs lumped together by type. And I think that's generally how we do it, which is you don't have to do every single one. But if you do lump, you probably want to do it by type, because that's going to give you the performance of one bioretention cell, as long as they're the same design, won't be different than another, especially if it's for one project and if the design criteria is all the same. So that's how I think of lumping, and when it's okay and when it starts to get a little more complicated.
Yeah. And the nice thing with this is it is a model. And so if you're unsure about an assumption that you're making, it's relatively easy to test it to see if it's sensitive. You can run it with 2 separate ones and then lump it together, compare the results, and see if it's dramatically different. It may influence how you choose to configure that.
Yeah, that's another great point, is that there's a lot of knobs, and sometimes you start turning things, you're like, oh my gosh, what did I just do? If you have time and if you want to be methodical about it, you can adjust, one thing, whether it's ponding height or diversion rate, adjust it and rerun it and see what happens. Adjust another thing, rerun it and see what happens. And we'll show you how to get through the output folders and files and see what that looks like, and be able to evaluate what is happening in the model. But that's a great point, John, is that like a lot of this is really hard to pin down what's happening in the model. Even we're asking ourselves pretty often on our projects is like, what is the model doing? And why is it doing that? And so that's when we have to pause and start adjusting things more slowly, or change things and look at the output, change another thing, look at the output again, and really dig in and get into the weeds. Because that is kind of the name of the game for modeling sometimes, is that we don't understand every single aspect of the model because there's so much happening, and the signal can get lost in all that noise. And so when you feel like that's happening, that's when you pause, figure out, all right, well, how do I maybe adjust or change one thing at a time and look at results, and so I can understand the different pieces that are happening and how they mix together at the bottom. Okay. So that being said, this is actual transition to exercise 2, which is configuring sustain. Now that we have sort of our mind starting to understand where we are in terms of drainage area, HRUs upstream, what does a project look like? What's the runoff time series that we have? We have a lot of what we need to run sustain. Now we've just got to get the model ready for that simulation. And so that's what this exercise is. So the first thing we need to do is download the executable. It also comes with a Microsoft update again. And this just allows Sustain's DLL to have a broader library of essentially code to run. So it needs this. And so you would download both those things. Microsoft update, again, you would need administrative privileges to install that. We've already talked about the HRU time series. It goes into a specific place on your desktop, because what you're going to do with your input file is say, hey, you're going to be looking for HRU runoff time series. It is here on my desktop. And so all the input files that I'm kind of providing as part of this tutorial and training, they're all over here. And inside of them, we'll get into this later in more detail, but inside of them, they're all pointing to a very specific location on your hard drive that it's going to be looking for these files. And so I've already placed those here. As you can see, the pathway in here is consistent with the pathway that we have here. And so inside this is actually one folder deeper, is those HRU time series. And so that's where they're ready and hanging out, ready to be called on by the model. So we put that in place because we already have it. Sustain, executable, and DLL, we've already downloaded those. We put those onto the C drive at this particular pathway. And then we set up folders, empty folders, essentially for model output and input to take place. Before I go into the next slide, I'm gonna jump over here to the information that we shared with you all. So through the calendar invite, we shared a link for a number of input files and folders. And so that's what this is. There's a README here that says, hey, download this, unzip it at this location on your C drive. If you need to create a WIMS folder, then do that as you need to. And this will contain everything you need to kind of run sustain as we're showing it here. So you would take this, unzip it, and inside of that, I don't know if this is going to open very well because a lot of my memory is being used by Zoom, but there's this folder configuration. I'm going to get out of it there because I want it unzipped, which is where we are right here. So I've just, in kind of this working or this format that we have here, I've already unzipped that folder. I've already got the LSPC. Actually, that's the model file right there. I've already got the LSPC data here. I've got batch files ready to go. I've got input files ready to go. And so when you all unzip this and download it to your C drive in this location, you can actually run sustain right away, provided that these your HRU time series are there. I'm pretty sure I gave those in that download. If I didn't, I'll go back and make sure that they're in there. So this, to me, this is kind of the command center. This is where action is happening in terms of execution of the model, where output goes. If I want to make a change to what's input into the model in terms of what's in the input file, this is where that happens. That's in this folder here. And so this is, my point of operation on the C drive is all happening in this. And we have kind of a, I don't know, to me, it feels kind of like a funny folder configuration, at least at first. But we use this current folder to indicate the current project at hand. And so let's say, we've done this project, it's a month later, and another project comes along. What I might do is actually do a copy paste of this folder and rename it and archive it. And so I won't do that now because it might slow down my computer because I've got a lot of data to copy and paste over. But I would copy paste this current folder, archive it, give it a new name, East LA Median Project, the date that we did it. And then I would rename this current folder. Actually, I would keep the current folder. I wouldn't rename it. And I would probably delete some of the things in here that pertain to the East LA Median Project and start kind of rerunning things or redoing the input files as I need to for this new project. And so kind of this folder, this current folder is always the current project at hand. And as you get new projects, you would just archive them and give them new names. So if you need to go back and say, that model you ran a year ago, which is sometimes what happens, and it's really sometimes difficult to go back in time a year and rerun a model and be like, oh, why did we do that? So archiving is a really important way to make your life easier as you need to do that. So with that, I'm gonna turn away from this sort of command center of files and folders that we have for sustain and get back into the presentation. Because this is the part where we're actually going to go through card by card of sustain. So now that we've got the folders and files in place, we've got LSPC run, the drainage areas and everything, we just have to put that into an input file. Like all the information that we have in our head or have in a spreadsheet somewhere, that just needs to be put inside the input file to run sustain. And so we already have these pre-baked, and so do you all because we shared this in advance. So I'm actually going to go back to this sort of launching point that I have here on my C drive for all my sustain stuff. I'm going to go into the input folder because that has all my different input files that I created. There is a short README here. It just says, this input file does this. And this input file is the same as that one, but it's just a little different. So I'll get into that a little later, but there is a README here to explain, like, why is there 9 of these things? So a bunch of input files. What John and I have done in advance to go through card by card how to set up a sustain simulation is we set it up so we can put it into an Excel spreadsheet. And to me, that's a much easier way of looking at things. Normally, if I want to change this input file, I will open it up in Notepad++, and I'll do that one time again because that was really fast. I don't think that's standard software on most computers, so if it's not on your machine, I would recommend downloading that because it's much better than Notepad, like the standard software that Microsoft comes with, and we'll show why in a couple of these examples. But this is a really great way to look through your input file. There's a control find and replace in here. It's just much better than your standard text file, and there's some compare options that are super handy. I've saved a lot of time using that function. So if you need to make a change to an input file, use Notepad++, but we're gonna use Excel to go through this example of a teardown. And so that's actually what we're gonna probably do for the next, I think, at least 30 minutes. So what I would say is buckle up. If you're taking notes, this is probably the point in the presentation that you're probably gonna take the most notes. And you're probably going to go back to this part of the recording the most because there's so much information in this input file that dictates to sustain when is the simulation, how big is the BMP, is there routing involved, what's the drainage area, what's the acreage of that HRU drainage area. There are a lot of details in here. And so we're going to go through each of those details that are most important. There are all sorts of details that are less important and we're going to spend less time on. So we're going to try and, bring the most important things up to the top, and then, mention the things that are less important, and probably, leave those for later in the presentation as we have time. But real quick, before we do that, the input file, just to kind of say it up front, is that it's a text file, but it uses a .inp extension. So that's just what sustain uses. It's really just a text file. Secondly, it's tab delimited. Sometimes you can have space or comma delimited files. This is delimited by tabs, and that's really important, and we'll show why. And then it's divided into sections that we call cards. So just like LSPC has an input file that's text-based, tab delimited, and separated by cards, sustain is the exact same thing, except those cards mean different things because we're in a different model now. So with that being said, I'm going to pop open this special input file that we created. It's going to go through each of these cards, like I was saying, and I've tried to color code it because without it, boy, this is just a block of text. Look at that. And this thing is 400. This is only one BMP. This is your probably most simplistic model that could be built. Because it's only one BMP, it's one drainage area, there's no routing. So from a sustain perspective, it's pretty straightforward, but that doesn't mean the input file is really easy to understand for someone who's never seen it before. So what we want to do is start with that simple case, show you where all the important dials and knobs are in sustain, how to change them, and give you a little more comfort, a little bit more, I guess, comfort in terms of working out of this input file. Because if, again, to go back to this example that I'm using, if Elon Musk is like, hey, I got a cistern I want you to put at the bottom of my big rooftop warehouse, this is how you tell sustain, what is the drainage area, what's the acreage, how big is that BMP, and you set this all up and you run it and you show Elon Musk and he's like, oh, that's great. You know what, can I have 2 BMPs now? Can it be wider instead of taller? Can it be like discharging at 0.2 CFS to a rain garden? And you're like, yes, I can definitely do that for you, because we know how to do that, or we're going to show you how to do those things where we set it up for one scenario, but almost certainly there are going to be changes where someone says, you know what, let's change this and let's do that. And there's a lot of fine tuning that goes on in here. And so what we want to do is, as you begin to do that yourself, seeing this more often is going to be helpful. And so we want to give you a lot of exposure to this input file before we send you all off to run your own sustained simulations. So with that, John and I are going to kind of ping pong back and forth going through the different cards. And the color coding I'll explain here a little bit. I added these boxes, these add borders. These aren't really here in the input file. I just did them for visualization. To me, they just kind of bound up the card. There is orange to indicate the first line of the card, which is the name and number. So this is card 700 model controls. There are 6 lines, which is these 6 right here of input, where the model is actually reading this row. And everything in green are things that we think are the things that really you should be looking at, because there's a lot of stuff to look at here. The green things are the things that you'll probably change pretty often, or are important because they can cause problems if you don't have those things correct. So that's sort of the anatomy of the formatting that we did here. In terms of each of these cards, it starts with the name and number of the card. It will start with a number of commented rows, and so everything that starts with a C is commented. So when Sustain reads this, if it sees a C up front, first character, it will skip until it gets down to here. So even though we read this, and this helps us, this is kind of the instructions of the card. Sustain knows what it's doing. It doesn't need to read that. All it wants is the information that you're giving it, which is these 6 lines. And so that's generally the anatomy is name on top, comments, which is instructions for us, which is these. And then you'll see those C's go away, and actually values are being put in place. And so that's where the actual parameters, design criteria, whatever it is being put into the model by you. And I just want to reiterate that we're doing this in Excel just because it's a little easier. We can show these colors and we can move around with a little more clarity. But if you're going to change something in the input file, that's where you want to go to Notepad++, and you say, and then this is the same thing. This is 700 model control. This is the commented line for instructions. This is the 6 lines that shows for card 700 what the model's reading, all the other cards, but it doesn't have that nice formatting. But in any case, if I wanted to make a change, if I want to do, instead of a 3-day simulation, I want to do a 10-day simulation, this is where that change happens. It doesn't happen in an Excel spreadsheet. It happens in the input file. I would hit Control Save, and now I've updated that model to reflect this changing critical condition that I've had here. So I'm going to do Control Z because I don't want to actually make that change. But I just wanted to be clear that we're using Excel as a visual tool, when in reality, adjustments to the parameters or variables is done in the input file, not Excel. So with that, we're going to go through each of these cards, and I think it might take about 30 minutes. It might even take 45. It depends. This is where maybe questions might come in handy. So I'm going to try and keep an eye on the, that raised hand function. If anyone has anything, I think this is a good place to say, hey, what is that parameter again? Like, how does that make sense? Because there's a lot in here. And we're going to try and explain everything, but there's probably going to be things that we miss or skip over, or maybe don't spend as much time as we need to on. So please, let us know if you have those questions. Almost certainly other people are having the same thoughts. So with that, John, I've done some talking for a while.
Oh yeah, I might add also, if you have questions, feel free to post them into the chat. And as we're going, while Ryan is going, if you have questions, maybe I can address some of those in the chat if we can do it directly there.
That's a great suggestion. Thank you, John. Yeah, so put those there. We'll look for them. John, I'm going to hand it off to you to do card 700. I don't think we need to go line by line up here. To me, it's just, what do these green things mean? John, if you think one of these should be green, we can kind of change it live and say, oh, this is important too because XYZ. But to me, it's the instructions are going to be here for you all to read them in the future when, we're not here for this presentation. What we want to do is say, well, this is where the input file, or this is where the output runoff time series from LSPC is being read. So that's that folder pathway that we've been talking about that houses all of those files, those 96 HRUs with those unit acre runoff and pollutant time series. That's where that is. And if you're going to put it somewhere else, that's fine. You just have to change that in your input file that and whatever that is, they just have to match, and that's all. Okay, so that's how I'm thinking of this, John. And I'll let you do 700 and we'll probably just bounce back and forth all the way down.
Awesome. All right, well, the first card in Sustain is card 700, and people are always like, why in the world are you starting with 700? Well, if you are an LSPC user, if you recall, the last card in LSPC is card 690. And the very first version of the BMP module was actually done in LSPC. And so we started from card 700 with the BMP rules. At some point in time, we realized that it was just bogging down LSPC to have all this BMP model bolted onto the end. And so we split it out of the LSPC model into a separate module, which ultimately became Sustain. So that's kind of the trivia behind the numbering there of card 700. But the first line in card 700, you'll see in there the option that is not highlighted, the 0. That is the external option. That's the only option that's available because external, what that means is that we are going to be getting our unit area time series from outside. So that's the way that we run Sustain now. We don't try to generate time series within the model. We take them from what LSPC has generated. So as Ryan mentioned, that folder there, that's the path that tells us where those files are located. The lines 2 and 3 are the beginning and end dates. Those are pretty self-explanatory. Line 4 tells us the land simulation time step. And if you recall, we outputted hourly. So that is in minutes. And so 60 minutes hourly there is telling us the time series time step. And then again, on that last element is our output. That's where we want Sustain to write the outputs of the model, the outputs of our assessment point, which is going to be at the BMP or downstream of the BMP. Line 5, you'll notice on there the first flag is 1, and the second flag, the second piece of information on this card is the file path. And so, yeah, exactly. So this tells us that that's our external evapotranspiration time series. So what that is another unit area time series that represents direct evapotranspiration. And the reason why we have this here is within Sustain, we load it with the boundary condition of runoff coming in. But depending on the type of BMP, if you've got vegetation in there that's going to be having an ET response, that time series tells us the potential evapotranspiration that can occur. Now, of course, downstream, you can parameterize that in terms of how much of that occurs and so on as a function of your vegetation and so on. But this is where you link that other boundary condition that you will ultimately use for vegetation. And then the last line 6, you'll notice it's all zeros. We're not using monthly ET coefficients in this case, because all of that is being governed by the pevt.txt file. So that is set card 700 in a nutshell. And again, all of these cards, we tried as much as possible to put a lot of documentation on what it is, what types of units were applicable to put for those terms. And so it's almost like a self-guided user's manual when you look at the card headings for each card.
Things I'll add, John, is like what I change in here pretty often. Like if I have multiple scenarios that I'm running, to go back to the Elon Musk example they were using, if he's like, oh, I've got these 5 possible configurations I want you to run. This is where I might, go in here to the output folder naming convention and go, well, I'm going to add V1 here, and then I'm going to run it as is. And then if we're changing something in the other cards, I will probably come up here and say, well, this is now V2 with this other change. If there's another change in terms of diversion rate or something like that, where we want to keep track of all these different outputs and what the difference is, that might be V3 now. And so that's something it's just an easy change that can be done here right in this this place in the input file. This gets changed, I think, pretty often. This is for doing a design storm, so you can see it's very short. But if you're going to do a 10-year time series, you would probably change all 3 of these things to get the year, month, and day right. 60 rarely ever changes because we almost always do an hourly time step, and I don't imagine anyone here deviating from that. But if you wanted to do a 15-minute time step, that's an option too, but I think we need LSPC HRU time series to also be in 15 minutes. So if someone says, hey, I want a more refined temporal time step in the model. I don't want hourly, that's too coarse. I want 15-minute because maybe there's something with QPeak that you really want to hone in on. You can bring that down to 15 minutes or probably 15 minutes is most common. You could do less, I suppose. But your HRU runoff time series has to match that 15-minute. And so you'd have to go back into LSPC, reconfigure it for 15-minute, which can be done. And then once you have those 2 things in sync, then you can run at 15 minutes and your output is now in 15 minutes. So there is additional resolution that can be gotten there, but we usually don't do it because hourly is in most cases sufficient and it runs faster, of course, than 15 minutes. Anything else on that card, John?
No, I think that's it.
Okay, so there's a couple. The following cards I'm actually going to largely skip. This is defining the pollutants. So this is where we say, hey, Sustain, we've got 7 pollutants. They are total suspended solids, total nitrogen, total phosphorus, cadmium, copper, lead, zinc. We don't expect that any of you will ever change this because you're in LA County and you're using the WIMS model and it's using these 7 pollutants, always in these order. And we've got the multiplier for total suspended solids set up here. So unless you're going to model something in Orange County and do different pollutants and kind of change your whole configuration, which we don't envision you all doing, that would be done here. But since that's not happening, I would save your brain power for the other cards where more changes are happening. 710 is another card where I don't imagine any of you all will change. This tells Sustain what are the HRUs in this model, what's their name, and what is the text file associated with them. So at this point, it's Sustain will open up this folder and it will look for these text files inside of the folder that we indicated that it's in. And it's going to read each one of these. It's going to assign a number to it. It has a name. The name is just really for us. Sustain could care less what the name of these things is. There's a sand, silt, clay fraction associated with them. Those are really model parameters that we've dialed in. And again, since we're going to be in LA County, you're always going to be using it at least or at most these 96. You'll never be using more. So this is, again, something I think you can skip card 710 altogether and say, great, the HRUs are there. They've taken care of it for me. I don't have to worry about it. 712 aquifer information. I've never used this once. I think this is one of those things that we Sustain was built with that functionality in mind, but we went a different direction and we just have never used that. And so John probably knows more about the history of that, but I don't.
Yeah, the aquifer, so that second column that we were talking about in the LSPC outputs, which is the groundwater inflow, that was there to connect with the aquifer. So if you wanted to catch all the water that's infiltrating in your drainage area, save it, attenuate it, and then release it back somewhere downstream in your system, you can build an aquifer into your model to kind of track water. Likewise, any water that infiltrates from the BMPs, you could send that to the aquifer as well. And then you can specify the rate at which the recession coefficient, the storage, you can specify the rate at which that water is released from the aquifer to some other point downstream in your network. So, yeah.
So in short, this is fancy modeling that we don't really need to do for almost any situation. So we can save that brain energy and walk right on by. Card 715, this is one of those ones where a lot of action happens. This is where you define all of the nodes in your model. And so we have it defined for our model here for the East LA project. There is an output junction. We have what's called an untreated junction, and we have the BMP itself. And so those are the only 3 nodes in the model. And if we want to add 3 more BMPs, they need to be added here and they need to be named. To me, what's important here is the name, what we call the BMP site, because anytime in the future cards where you're saying this BMP is 100 square feet in footprint, you always have to refer to it by its name. And that's always done in this first column here. So we'll show some examples in other cards where that's happening, but the name is really important. And then the BMP type is quasi important. There's really two types in my brain of BMPs. There's junctions, and then there's everything else. We could have called this, instead of infiltration trench, these are all the options up here. We could have called it bioretention, wet pond, cistern, dry pond. You're almost always going to want to use infiltration trench as your BMP type of choice, even if it's a bioretention cell, even if it's a wet pond, even if it's, let's see, porous pavement. There's only very few instances in Sustain where you're going to want to change that to a cistern or a swale or a rain barrel. There are different rules for those. Since that's not in this project, we're not using those, and I don't suspect that you all will encounter that either. So we're using infiltration trench here for BMP type under this header, and I would think that for all the projects that you're all using, you will do the same. The other junctions up here use the BMP type junction. So this indicates this is not a BMP, that it is in fact just a place in the model where we put a node. And so if I wanted to, I'll draw the routing network later, but in my mind, there's a BMP at the top, there's an outlet on the bottom for all outflow, and then there's the untreated node if we choose to use an untreated node. It's always there just as an option. So we don't actually necessarily need to use it, and I'll get into that in the future cards too, but this is really just setting up what are the nodes what are the nodes and BMPs I have in my model. Do I want to add another one? So let's say in this kind of continuing to use this Elon Musk example, if he's like, you know what, I want to use 2 cisterns and they can't be lumped because they're so distinct and different from one another that they have to be characterized separately. That's where we would say, all right, well, I need to rename it. It's cistern 2. And I'm going to take this whole row, I'm going to copy it and paste it down. And now I've got a second BMP type. It's got its own name. It's the BMP type infiltration trench, which doesn't really mean anything. It also has these other things: D area, number of units, TD area. These are sort of explained up here. I don't think any of you will ever kind of adjust this. You may go up here and adjust the number of units. So if you want to essentially duplicate this BMP, you can put a 2 on it, and it will now model 2 of those side by side. So if, essentially the footprint is doubled for that BMP. This is usually how I don't think John either does this in modeling. We don't usually use number of unit to indicate square footage or anything. We always use the square footage in the layer card. So I think 99 times out of 100, this is what these columns will look like. Even these ones over here. Actually, even these ones over here. It's really just the name of it, with it, it's being introduced, is 715. So we've got a question, actually maybe a couple. So what would we use if it's a biofiltration flow through like our BMP, lot BMPs? Would it still be infiltration trench? Yeah, that's a really good idea, because in my mind, an infiltration trench is not a biofiltration flow through BMP, but in this card they are. Almost any BMP type, unless it's cistern, rain barrel, or I think even green roof, swale. There are particular rules for how those are handled, and you introduce that up here up top. But if it's a bioretention cell, if it's a regional infiltration, regional filtration, diversion to sewer, porous pavement, any of those BMPs, it's always going to be infiltration trench, or it can be bioretention. I don't want to make it too complicated by saying you could do all these things, but I'm saying infiltration trench just because if you stick with one, you're good. You've got it. Anything else you want to add to that, John?
Yeah, and those reserved sort of BMP types at the top, think of them as just conceptual, because it does just control the types of knobs that you will be able to turn later on. So bioretention, infiltration trench, those ones give you access to any of the knobs. Then you can go in and decide, okay, I'm not going to have an underdrain layer, or I'm going to have no soil media. You can make that decision. But if you choose rain barrel or cistern, the reason why those are there is it protects you from accidentally adding a piece of the model that shouldn't be there when you intended it to be just a storage device. So they're just there to kind of help with configuration. But for most maximum flexibility, it doesn't really matter what you call it, but those options for bioretention, infiltration trench, and so on will give you the most flexibility.
There's a follow-up question to that one. What if it's a train of BMPs? And to me, to answer that question, it depends on how those are being characterized in the BMP. If it's a train, let's say like a 10 infiltration wells in a row, we'd probably just lump those and use them as one line item in this card. If you've got a train of 10 infiltration wells and then 5 bioretention cells, and then so on and so forth, each of those groupings, each of those aggregations would be their own separate item on this. And so if it's its own node in the model, then it's introduced here as such. And that node is either a junction, or that node is either a BMP. So it might be easier to explain that through an example. So we can bring it up again when we get to that actual output of the model.
Yeah. This card is really for defining the different footprints, different instances of BMPs that you have. The treatment train option, there's another card later on where you define the order in which they're connected.
Right. And then I guess the last part of this, it's good thinking about, is that the different treatments that might be available on these different BMPs. So this is, again, how can you lump BMPs, and can you lump BMPs? If you've got, like if I've got one project, but it has multiple components, I actually may break that out into separate lines, because I can't divert to sewer. I can't divert to sewer and be a swale and have infiltration. And I mean, there's certain things you can't stack onto one BMP, and you do kind of have to break it out into several BMPs. I don't think we're going to be doing anything too complicated like that, but there is an option to do that, and that would be for every BMP that you break out into a separate BMP in the model. That's done here in 715. So, for example, I'll do this again. If I wanted to say, well, there's this other part of the project. It's still the same project, but I can't characterize them in one BMP because it's so different and distinct. Maybe it's diversion to sewer. And if it has diversion to sewer and an orifice, that's actually two things we can't do in the same BMP. So you actually have to break it up. And so I might kind of just duplicate this whole row again. And this would be, I don't know, 1 or B or something like that. And so now I've got two different nodes in the model, and I can characterize them separately. Hopefully that wasn't confusing to add that layer of complexity in there. But yeah, by and large, card 715, you're just introducing your BMPs. If you've got 2, you're probably just going to have 2 in here. If you've got 1, you're almost certainly just going to have 1 BMP in here. The outlets or the junctions, you can either keep or leave in here. I always just leave 2. And whether you use them or not is dictated in the routing network. And we'll show that next.
There was a question about how are projects that feature diversions to sewer and or treat and release modeled?
I see that. We are getting there. I can sense the excitement. Tell me about this. Tell me about this.
I know, like I'm hearing you, Ryan, and I'm like, hey, how are we doing these scenarios? So I'm glad you're going to touch on. I just wanted to understand like how that works from a modeling standpoint. So, all right, cool.
This whole thing, TJ says that's all we want to know. So yeah, great. That's a great question. We are going to get into it. I don't know. I feel like we're trying to step through this really slowly because it is so much. And so we are really on the first card that just says, hey, there's a BMP and there's 2 junctions. That's all this card says. And if you want to add a BMP, you add another line. And for the most part, you just copy and paste the line above and just add a name for that new BMP. That's all card 715 does. And I know that's not very exciting yet, and we're getting to the good stuff, I promise. The next couple cards, C721, 722, pump curve. I kind of want to skip those altogether because I've never used them. I don't think any of you will ever use them. Just ignore them. 725. This is a big one. There's a lot of action happening in 725. This is where you start to define what that BMP looks like. And again, there's all these commented things above which pertain to, these parameters across. And so if you're ever like, what is width? Well, that's just the bottom width of the basin of the BMP. And that will be the infiltration area of that BMP. So there is maybe width and length is sometimes more complicated than it sounds. You may have a big footprint, but if your infiltration area is really small, that's actually what Sustain is asking for here is what's your infiltration area where water is going to be going through, because that's going to dictate how much can move. If you've got a big footprint, you can move more water in an hour, but if you've got a small footprint, you can move less water. So that's width and length. And if you've got, this is where it gets a little complicated, but if let's say you've got a really small patch of infiltration area, but you've got a huge BMP otherwise, it's probably not common. But you have to think about, well, I have to have the footprint the same size as the infiltration area if we're infiltrating. I have to take that volume and kind of move it somewhere else to make sure that capture area is there. So that's kind of a special case. I don't want to spend too much time on that unless maybe at the end if we have time. In any case, width and length, almost certainly you'll be changing these a lot. We have an acre here being represented. So if I multiply this times this, I'm going to get 43,560 or thereabouts. And that's an acre because that's the size of our BMP. Orifice height and diameter, I have those light green. Probably not going to use those very much, but sometimes if someone's like, hey, I want to put an orifice height here, if it's a certain type of detention with flow through through a diameter or a fixed diameter outlet, that can be controlled here. So what's the height of it? Is it a foot up? Is it 5 feet up? That changes the pressure head on that BMP as the head of the water in the BMP changes. The diameter, of course, that's just the equation. So if a bigger diameter means more water. Exit type, release type, heat pool days, weir type, almost will never change. I think we can skip over that. Weir height and weir width. Weir height is just the height of the BMP. So these three things, these are the dimensions, most important dimensions: width, length, weir height, which is the same thing as ponding height. So if someone says, yeah, in feet, thank you. If someone says I've got a 2 foot ponding BMP, well, then you put 2 here. We have a pretty big ponding height, so we've got 22 in here for our weir height. Weir width, John, I think we actually don't really change this very much anymore. In the older versions, we used to make this really big because if you get to a certain height on the BMP, if you're spilling over, you don't want to be restricted by a width of your weir. If it spills over, if stormwater spills over your BMP, you want it to spill unrestricted. And so we used to put it as a very, very wide kind of, I wouldn't say nonsense number, but it would be so that there's no restriction here on the weir width. This is getting a little weedy on the model, but I think we've updated, so this number actually doesn't really matter as much anymore. Is that right?
Yeah, it's a little less sensitive in this case. You just want the water to be able to get out quickly when you have exceeded the capacity.
Yeah, imagine the way Sustain thinks of it is if you've got a weir width of a foot, it can only let water leave at that foot width. But in reality, you've got the whole BMP, I don't know, perimeter that is probably spilling out over. So you could use that. I always just use something arbitrarily high because the model could stack up water above your BMP. So even though your ponding height is 22 feet, if you have a narrow weir width, you're actually going to restrict flow out of your BMP, and that water will stack above your weir height, which in reality doesn't make sense. The water would just spill everywhere if it were implemented. And so that's why I usually keep this number really, really big, because as soon as water surface elevation in the model gets above 22, we want it to spill out. We want it to leave, because that's what's going to happen in the model, or in reality, in most cases. There's a couple other things down here. I wouldn't worry about these. ET multiplier is actually maybe of consequence. I would put light green on that. So John, if we're doing a bioretention cell, I would put ET multiplier at 1. And that means we have ET in this BMP. And so when we read an ET time series from LSPC, it will actually draw out some of that, moisture, that volume of stormwater out at the rate that PET is happening according to that file. But let's say you have a subsurface totally contained infiltration well. Is there ET happening in there? Probably not. So that's when that goes to 0. There's some other things in here. This is, well, John, I'll let you explain the bypass because you're describing this earlier, and then I'll do the div rate and we'll move on from this card.
All right, so the bypass flag on here, it says the fraction of the inflow that bypasses when the BMP is full. And so in this case, we have the bypass flag set at 1, which means that once you have filled the capacity, meaning the whole footprint times the weir height of that BMP, once that is full, any new water that's trying to come in is going to bypass and pass the BMP and go directly to the next node downstream. I talk about node, and I talk about this going back to what we were discussing from the previous card where we said, hey, here's a BMP. The cards and the order in which these are sequenced is just pieces by pieces. Think of it like a box of Legos. 725 is the surface storage ponding piece of your BMP. So all the terms that you've seen up here, we haven't seen anything related to soil. We're just talking about control structure, what's on the surface, what happens when new water tries to come in, whether we let it come in and mix and overflow, or we let it bypass if we don't have any space for it. And then the final one, the diversion rate, that is starting to answer some of the previous question that was asked about diversions into or out of this BMP. That's the rate at which water can be diverted into this facility. And so any water that is beyond that rate goes to the next downstream node. Now we have a decision to make downstream as to what happens with that downstream node, if that's going to another part of our network, if that's going to another facility, we have the ability to define that. But at this point, as far as this particular BMP East LA project is concerned, we have defined the piece of the puzzle, which is just the surface compartment.
Right. There's actually one other thing. It's not listed in here because this is an older input file. We haven't updated, but there's a secret release type 4. So let's say I'm going to do a project that releases, actually, this is a project that releases at a fixed effluent rate. So if I've got, there's a couple of different ways to handle this. If I've got a sewer diversion, I will change release type to 4. And then I'm pretty sure it's orifice diameter. I'll have to confirm and check and probably email you all afterwards. But I've changed release type to 4, which I'm sorry is not specified in here. I'll try and get you all an updated one which says 4. And then I'm pretty sure its diameter is in CFS. So if I want to release at 3 CFS to somewhere, I changed release type to 4 like I did, and I'll change this to 3. And so now we've got a diversion rate of 8 CFS, or rate of diversion of 8 CFS going to this BMP. It has a volume, and it's going to discharge at as much as 3 CFS to a downstream node. And so what downstream node that is handled in other cards. But this is the first part of setting up either a sewer diversion, or you can also use this for sometimes if you want to model a fixed discharge rate for like an infiltration well and say, well, on average, one infiltration well is going to do 1/4 CFS exfiltration, and I've got 5. Well, I can just multiply that by 5 and do 1.25. And instead of doing infiltration as an infiltration rate through surface area, I've done that instead to this right here. And John's got a box I think he's drawing.
All right. So here is our diversion rate that comes into the BMP. And what Ryan is describing is we can have an orifice. Now, in this case, if we use this release type 4, then we change this discharge rate as an orifice outflow. So that's the rate at which it's going to come out of here. There's still another outflow, which is when this thing is full, we're going to overflow the weir. And so that's the weir outflow. And so we have one flow rate coming in, and then we have 2 different outlets. And you'll see later on, we haven't talked anything about what happens because we can bolt another piece on here, which is a soil layer. We're going to get to that. If it's applicable, then you have an underdrain outflow and so on. But as far as what we're seeing in this card, we're just talking about the surface piece right now, which has 2 ways out, at least for this BMP type that we've specified. So you can imagine if we had other BMP types, let's say we had a cistern or a rain barrel, those also have surface rates, but the way that those happen are going to be slightly different. Because in a rain barrel or a cistern, you have other parameters that can be used to decide how the water is released. If you've got a cistern that's being used for gray water, purple water recycling in the house, for example, then that cistern is going to be used for toilet flushing. You might have a diurnal pattern that shows when is the water being reused and how many people there are. You can specify that, and that's going to be used to decide how the water is released and used downstream. But this gives you that feeling of, these are the types of knobs that we have to turn. And for this case, these are the two outflows that we can work with. And later on, we'll see what we do with those two.
Okay, so as you all can see, it gets complicated really quickly. I'm gonna show another. I'm gonna show another input file. So I apologize. This header is actually slightly out of date. I'll get you all a new one so you have it. But this is what the updated header looks like. So it has release types, the same exact thing, but we have this number 4 option, constant release rate, which is, let's see, release type here again. Nothing in here is using that. And then I've also got diameter. So normally it's orifice diameter in inches, but if we're using release type 4, then it is a release rate in CFS. So again, if I go back over here, I've changed the release type to 4, and now I'm releasing at 1.2 CFS. So that's the max a value that it will release at. If there's more water, it will slowly drain that down. But if there's less, it will do all of it until it's empty. So that's how that works.
Yeah. And that maximum also applies to the inflow, the diversion inflow rate. You can only send water into it at this rate. If there's water coming from upstream that's higher than that, then the difference just continues downstream to the next node in the system.
Okay, I lost my chat, so if I can't see it right now, I'm going to try and get it back up as we move along. So I may miss things, but John, if you see something, let me know.
Okay.
So cistern control. By the way, John, we have about an hour and 20, so I just want to keep that in mind. I kind of want to wrap this up in 20 minutes, and that'll give us an hour to do questions at the end for maybe 15 minutes, and then be able to run the model and look at output in maybe 30 minutes. So we're gonna start to compact some of the stuff now. So card 730 cistern control. I don't think we're going to be doing that, but we can skip that. 740 is another big one where now we're starting to get into the soil vegetation. So that the second layer, soil and vegetation characteristics. Again, we've got that BMP site here. So it's telling me this is the BMP for which these parameters pertain. Most of these things, I don't think you can adjust. So it's just the ones here I have. Soil depth. Is there soil depth? 0 if not. And if you've got 5 feet, it's 5 feet. If it's 2, it's 2. I'll change that back to 0 since we don't have any here. Fin filt is the infiltration rate of the media in the BMP. And so we have 4.63 inches per hour for the native infiltration. So we're actually going to use that over in this parameter value as well, because we don't have any other, we don't have the under drain on. And this is where it gets a little complicated too. If you're going to use an under drain, it's kind of a question you ask yourself before you start this. And if the answer is yes, the switch goes to 1. The next thing here is, well, how deep is that under drain depth in feet? Let's say it's 1 feet. What's the void space between the aggregate in there? Usually it's 0.4. And then the last one is, what's the infiltration rate of the native, what's the infiltration rate of the native soil surrounding the BMP or surrounding that infiltration rate? And let's say it's lined, well, this stays at 0. Let's say it's not lined and it's going to be infiltrating at the same rate as what we have here for the media. That's 4.63. So now I've added an under drain by just turning the switch on, giving it a depth, specifying the aggregate void space, and then the infiltration rate underneath it. And so that card controls this aspect of that, the under drain part of it. The media on top, what's the percolation rate or the flow through rate? There, and John's going to be drawn while I keep describing. And there's the soil depth again, right on top. How deep is that soil? That controls, volume. There's porosity there, which is this next one, which I don't think you'll change very much. So that's why it's not green. Field capacity, wilting point, probably also things you won't be changing very much. I do have average or vegetative parameter. This is more for if you've got bioretention, and I'll let people look up what the vegetative parameter is for Holton infiltration. But you can dial up or down vegetation. So if you've got really rich bioretention cell with a lot of vegetation, you might dial this up to 1 or 0.8. If you have no vegetation, well, that's 0. And that dictates, how much pore spacing there is created by the roots. There's also a growth index here. That's done in the next card, but these two are kind of related. It's about vegetation, whether it's present and how robust and healthy and active it is. Because the more you have, the more it will draw stormwater out of that bioretention cell or whatever the BMP is. If you don't have any, the answer is really easy. It's 0. If you're subsurface with no vegetation, you're always going to be 0. Even a sand filter that's subsurface, I would still put this at 0 because there's no vegetation. So that is that there. And John has drawn this nice diagram here where the soil is just kind of this flat layer, and percolation rate is that 463. How fast does it move through? And if it overflows, if there's no more space in that soil depth, that volume, it will overflow. And anything that makes it through, and if there's an underdrain, it will go through that underdrain. And if not, it will go right to the native soil infiltration at this rate. The one thing I think is useful for pointing out is if the underdrain is off, this is your native soil infiltration. It's also your media. It has to be both. And so if you have a soil that's 5 inches per hour, like your media, your geomedia that you're buying, and if you've got your native soil is 2, well, do you put 5 or 2 here? You always put the native, which is 2, because that's what's restricting the performance. If you put 5 here, then water's leaving through the subsurface at a much higher actual rate than what would be happening if it was implemented. And so I'll just say that again. When no underdrain, this is your native soil infiltration rate. If this is on, you can actually put that number over here, and you can do this to whatever you want. You can put this up to 5. You can put it up to 10. All that is controlling now is how quickly does water get to your underdrain. And once it's there, that's what the native soil infiltration rate does. Does that sound right, John?
Yeah, that's right. And I just want to mention, there are 2 layers here. There's the soil layer and then the underdrain layer. So like Ryan is mentioning, in this case, we don't have a soil layer. So this whole piece is gone. That's why this term governs everything. If we did, then this would be the rate at which water can pass through the soil layer. This is the rate at which water can leave at the bottom of this. We specify the underdrain height when we have this. And you'll notice there's nothing describing the control structure out of the underdrain. That's because in sustain, the rate at which this happens is so small compared to what's happening on the surface that once this underdrain storage is filled, then we have overflow. The overflow outlet for the underdrain is at the top of the storage. So as long as we're less than that, we're going to have water percolating at this infiltration rate. And so this is 2 different pieces in one card. And how we've described it, this is 0. So this top piece is gone. And then this is our final infiltration rate. So this rate that's going through here is the same as the rate coming out at the bottom.
Okay, perfect. And I'm going to change these back to 0 since that's what these were before. So I'm going to move through to the next card. Reference it a little bit, the Holton growth index, since we are using Holtan as an infiltration method. This is subsurface, so it's all zeros. There's 12 zeros here for every month of the year. So you can get really specific with, there's a lot of growth index in spring and summer months, or maybe mostly just spring, and not so much in winter and not so much in fall or summer. You can specify that here. 9 times out of 10, if I'm going to use this, I'm going to pick one value, and I'm probably going to move it all the way across. and do it the whole year, the same thing. One, because it's California. We don't have harsh winters like the Northeast might, where your plants are going to be covered in snow, and we don't have a low latitude where you're going to get little sunlight. So there's not that much variation here. It's also, the model's not very sensitive to this. So if you jack this all the way up to 1, put it all the way to 0, it's not going to make a big difference, or not too big of a difference. And John's pointing out the function here. So this is a value inside of this Holton equation for infiltration. So it's a multiplier that goes up front.
Yeah. So the key driver here is going to be the final infiltration rate and then the computed available soil storage. So all this does is, if you plot this infiltration curve, at the beginning, when you have a lot of available soil storage, infiltration will be high. And then over time, it will reach this final infiltration rate asymptotically, because this is a nonlinear equation. And so that's the simple construct. It's pretty handy because we have all this information. We know how much soil storage we have. When that is full, we're going to approach our saturated infiltration rate, and that's it. So this coefficient just gives you a way to kind of modulate that seasonally if you want to. But it's a pretty simple infiltration function, and for this purpose, it works pretty well.
Okay, great. I'm gonna keep us rolling. This is initial soil moisture content. You know, usually these BMPs aren't totally dry, so we have usually as a default 0.15. So there's a little bit of moisture here to start with. Instead of a spin up, we start with this. And so if you're gonna add BMPs, what I would do is just take that name. Oops. You can insert new ones, add the name, whatever it is, and then just copy paste this thing down and move on. Since we don't have much time, I'm gonna kind of just leave it at that for this one, because it doesn't play a big role in terms of performance, and then we always use that same value anyway. Class 750 conduits, we're not gonna do anything there. Regular cross sections, no. Buffer strip, no. You'll notice that there's a lot here in the middle that we're not gonna do. Area BMP, no. This is a little more actually useful. I think we should mark this as something that people should stop at. We always use standard pollutant decay and loss rates. And so this is first order decay, and this is the values for it. We always use the same number for every pollutant. If you want to get really picky and dial this in and use different decay rates for these pollutants, and the pollutants are in order that they appear in card 705, I think it is, the pollutant identification card. This is pollutant 1, pollutant 2, pollutant 3, pollutant 4, 5, 6, 7. I would never change these. If you're going to add BMPs, I would probably just drag and drop these down, because there's some amount of decay happening at a very small amount. You can tell these are pretty small numbers in these BMPs. So there's that. That's just kind of a standard pollutant decay loss rate. I think this is Cadillac and Knight. Yeah, I've never used Cadillac and Knight. This is another way to assign performance to the BMP, and there's a couple different cards for it. This is one where if you don't use this performance removal method, you can just skip it, and you can see that it's blank here. There's no BMPs here. Card 767 is about again, Cadillac and Knight. We can skip that. These are a little more important to me. This is for release type 4, release type 1, and release type 2. So there's different types of underdrain. So it's not so much enough to define that you have an underdrain, but if there's removal applied to that underdrain, what is the type of removal? And so here we have the BMP copy pasted 3 times, one for each of these card removals. And I can only do option 1, option 2, or option 4 in this case. I can't do multiple. Sustain isn't capable of doing that. So what these are is, again, it's kind of thinking about your BMP and what it looks like and what it's doing. Is it removing pollutant removal at a percentage, like a consistent percentage? Sometimes you'll see for pre-treatment proprietary BMPs say that we remove 80% of TSS. And if that's the only information you have, you can actually put that in here as a percent. So in this case, it would be 0.8 for this pollutant. That would be TSS, this is the first pollutant. If you don't have those values for other pollutants, you just leave it at 0. If there is no reduction for phosphorus by a certain underdrain, then it's left at 0. So that's controlled here, percent. There we go. A couple questions. Can we treat the underdrain as a treat and release, like a modular wetland? I guess it depends. I don't know, John, what are your first thoughts?
Well, you have an effluent concentration that you can specify. And so if you know that all the effluent coming out at the constant flow rate is at a certain level, you can do that. You can say, this is what is going to happen. Out of this BMP, we're going to treat it to this level. That gives you, some protection and some flexibility there, because you don't necessarily have to model the full mechanism of treatment. You can use empirical data that you've collected about your effluent to define what's happening coming out of the BMP.
So yeah, two things. One is that for a modular wetland, what I might use, and I think you were saying this, Sean, is that I might use release type 4 and say, all right, well, I've got an orifice here and it generally discharges at 2 CFS at most. And I can apply a treatment to it, a concentration in milligrams per liter. So if the treatment from some research that we're taking from somewhere else is 13.2 milligrams per liter for total suspended solids, concentration will not leave that BMP through that orifice at concentrations greater than that. It will treat everything else, and it will discharge that rate. So if 18 comes in, 13 will come out. If it leaves through 13 milligrams per liter of TSS will leave through that effluent orifice. And you can specify that for each of the pollutants. Again, if there is no treatment, it's just 0. There was another really good question, and I'd never actually thought of it this way before. Like sewer diversion, do you put that at 1? I would, at first I was like, yeah, you could. That would do it, I would treat it. The only problem is, let's say you're building this facility, where does that treatment go? It doesn't go back to the river, it goes down to the treatment plant. So it actually leaves the system altogether. So that water will not commingle downstream with anything else. And so what this is, if you're doing an underdrain, that underdrain, the water will get treated and then it'll go back and be commingled in the channel, which in most cases is fine. But for a sewer discharge, you wouldn't actually handle treatment here. You kind of handle it in a hack. And we'll show you that hack when we get to 795. So we've already handled it up top in card 740, I think it is, with orifice size, which is the discharge rate, and then release type 4. So we've already set those two things up top. So we've already made it a release type for sewer discharge. The next thing is, where does the water go? And that's handled in another card. So yeah, we'll get in there. But good question. Yeah, really good question though. TJ's getting at the answer already at Dummy Junction. Yeah, you set up a sewer junction and you're like, this is just the trash junction. Anything you wanted to disappear, you send it to this node and the model will never see it again unless you put your outlet at that point. Or if you put I guess it's your outlet in the last card. And that's kind of like your dummy miscellaneous trash. Just send things away if you want it to disappear. You have to be really careful with that because you're letting effluent disappear in the model, which is, if you intend to do that, then that's perfectly fine. But if you start sending flow there that you don't mean to, then you're going to have flow disappear and you may not know it unless you're actually looking at that outflow. So good question.
Yeah, and this is really a good discussion because it can matter when you're using this in the well, we're not doing optimization here, but if you're looking at performance at some downstream point, And you need that dilution to help you with achieving your objective at the downstream point. Then sending water out changes the equation. So you have to consider, is this the real representation? If the water is being diverted to be sent somewhere else, that's just the reality of the system. And we just recognize that it'll change how much water and how much pollutant goes downstream. And so, depending on whether you're removing more water volume than pollutant load, that affects the concentration downstream of this whole BMP or network.
Okay. So just recapping on everything we've talked about, this is how to assign treatment through the underdrain. If you don't have an underdrain, this doesn't matter. The model doesn't see it, the model doesn't read it. Water will go into the BMP, go into the soil, and if there's infiltration, which there presumably will be since there's no underdrain, treatment happens through the subsurface, which means, since that model also, or that water also leaves the model, there's 100% treatment of everything that's infiltrated. So that treatment is handled in that way, sort of just by default. Underdrains are handled here, and also release type 4 is handled here, which isn't actually an underdrain, it's the orifice treatment. And so that only applies when that's selected to 4. And so if you're using the standard orifice, which is not present, option 3, you won't use this. I'm going to go back up real quick to card 740 and show that underdrain treatment option. Underdrain switch. So I kind of glossed over this. Underdrain switch isn't just off and on. It is either off or with removal, percent removal, or with constant effluent rate. So there's 2 types of on. So if you're doing 1, if you say 1, you're telling Sustain, I'm doing percent removal. So 80%, 70%, 20%, whatever it is, that's what I'm going to do. And then in card 777, whatever it is down there, that's where those numbers have to show up. So Sustain will connect those 2 things. If you don't want to do that, you want to do constant effluent rate, that's 2. And that's where you're saying whatever leaves, it can't be bigger than this number. And that's, of course, that number is going to come through other sources. Some sort of research will dictate what that value is. And so again, that's where we handle those values.
Yeah, so TJ asked if you can do a percent reduction for an orifice. If you're talking about orifice as in something that's coming out through an underdrain, yes. Other than that, you can't. But what you can do is you can specify the treatment through the outlet when you have that fixed outlet for the orifice. That one can be used in the case of release type 4 on 768. You can specify what the release concentration is. So it's not a percent removal, but you can specify a treated effluent concentration through the orifice.
The other thing, so there's a couple different ways to get at this. So there's not, like John, you're saying, there's not a straight percentage that can be applied. And it looks like TJ is saying they usually work in percentages. So we're kind of constantly trying to add new functionality. Card 768 is brand new. And so we weren't able to do that. We're still I think ultimately we want to add concentration as a function. What you could do instead to get around that is you could start to use a pollutant decay loss rates, and you can parameterize these to get at a percent reduction. It won't be perfect because depending on that retention time that stormwater is in at that BMP and the storm size and all these other considerations that are happening, you may not get the same exact percent, but you could draw these up or draw these down to get a higher pollutant decay, and that will get you maybe closer in general to that percentage that you're after. And so you could hack at it and use the model and parameterize these values to get an average percent reduction, which is the percent reduction that you're looking for. But you couldn't just say 30% all the time everywhere through the orifice, you would have to use the decay loss rates, which are in units of per hour.
Yeah, and that's always a tricky thing with this. We're trying to stay on a process-based representation. So, per hour unit means that you're going to get more treatment if you retain that water longer in the BMP. So if you have a huge storm that just blows right past through, it doesn't spend a lot of time, you're not going to get a lot of removal. So yeah, it's a balancing act. The effluent concentration, typically, where people are requesting, that this whole edition of card 768 was added because a lot more people are asking, we have data about the performance of our BMPs in terms of effluent concentration. Why can't we just put that in? I said, okay. And you can always do some desktop analysis to figure out what that translates to on a percent reduction on a long-term basis. You can specify an effluent concentration to get at something like that. But the goal is here trying to keep it process-based as much as possible, recognizing that sometimes percentages can be too flat when you apply them because there's not that time dependency associated with it. But the other thing to mention is this BMP still, these rates through the treated effluent, through the release, these outlets are a relatively constant rate. If you have a huge storm that comes and it inundates the BMP and you have a lot of bypass, you're not getting a lot of treatment anyway. So the importance of these diminishes when you have overflow, because when you have overflow, then you're getting essentially your outflow concentration is closer to your inflow concentration. So over the course of the simulation, you'll see larger events that blow past your BMPs will have lower performance. We're trying to get at that process-based texture instead of just one flat percent removal. It actually gives you that it depends the kind of answer that you would want to see from a process-based simulation model.
Okay, great point. I'm gonna start moving past the underdrain stuff. There's a number of other cards that really we don't adjust or play around with too much. The next one that we're gonna talk a little bit about, but again, I want to keep it brief because we are in the final 54 minutes of the presentation, is that we've talked about the BMP and we've pretty much set the BMP up in the model. We know what it looks like, dimensions, height, treatment if there is any soil, so on and so forth. And now the rest of it is, well, what's the network and what's the model environment around this BMP? And so this is looking at the upstream drainage area. And so this card can get really long. The first column is just a counter. It really does nothing except count. So if you're going to add to this, all you do is count down further. The land type area, this is going back to card 710, I think it is. Yeah, there you go. Thank you, John. And we define land type 1 as HRU 1000 road type freeway or something like that. Land type 2 is HRU 2000 road type primary, 3, 4, so on. So we have a code up there in card 710 that this references to. And so what we're saying here is that there's 22 acres of this HRU. There's 46 acres and change of this HRU, so on and so forth. If you're going to do a different project or a different acreage, this is where that change is made in the input file. This can get pretty complicated pretty quick, especially if you have multiple nodes. If it's just one downstream project, which is what we have here, it's all going to the CCLA project, then that's pretty simple. If it's actually 10 acres instead of 22, and that's just a switch right there. And if you're going to do a different project, you'll probably use something like control find in Notepad++ and change East LA project to something else. And then you can start keying in these numbers. You notice that there are skips here. There is no HRU or land type 11, 12, 13, or 14. And that's okay. It's just not present. There will be other models that you run that do have those and not others. So you do have to keep track of, well, I've got 22 acres of HRU 1000, which is road freeway, I think. Got to make sure that you're using land type 1 here to represent that. And so yeah, just going to say that the acreages and the land types and HRUs have to line up, and that's where they're done here. And the downstream project is just the name of the BMP name that we've been using in all the other cards. So in this case, I'm going to highlight this, and I've got, I can't see it here because of the size of it, but I've got 2,900 acres going to East LA project. And so you can always do a check right here and say, should there be 2,900 acres? Should it be bigger? Should it be smaller? And so that gives you that sum right there.
I'll mention on here, this is where you really can go to town with representing how your network is set up. And in most cases, in this case, we have all the area going to the BMP. In some cases, you're going to have some untreated area in your assessment area. And so in that case, you might have the HRUs that are not treated, like all your forest areas that are not necessarily upstream of your BMPs, but you still want to count them in your total assessment point. You'll send those directly to the most downstream outlet. So in here, you'll have, it won't just all be East LA. Some of it will go to most downstream outlet. If you have another BMP, you put that. If you have a treatment train, you put the first area that goes to just that BMP, because later on, there's another card that specifies how the BMPs are connected together. So that, you can imagine, you can get that treatment train effect represented. But at this card, you only put the area that is the part of the immediate drainage area to that BMP in column D.
So that's a good point. Adding on, John, like if we have a hypothetical where we have, I don't know how many acres this is, maybe 35 acres, all of this one particular HRU going to untreated. Actually, what we would do instead is do this. This is a lot easier. This is the HRU number, which goes back to the name of it or the type. I've got the counter here going one more down. This is the acreage, and this is what it's going to. So untreated. Now we just added untreated area to this network because we happen to be in an area where the diversion point is upstream, and we have this untreated amount that's always untreated. So that's probably a pretty regular change that you all will do, where you're going to be adding to this, and all you do is add what's the acreage, what's the land use associated with it, count down until the bottom of this table, and then what is that downstream thing? Is it an outlet? You have to use that same name that's in card, I think 715, because if you start to use an ID that it's not familiar with, like dummy, it's going to say, hey man, you're using a node that you have not introduced in that upstream, that other card 815 or 715. And so that needs to be introduced there. And so that's where you would do that. That's what we were talking about earlier. So I'm going to delete that because that's not this project. The routing network, to me, 790 and 795 I'm glad they're placed right next to each other in the model, because in my brain, they also sit right next to each other. Above in 790, we just said there's this acreage going to this most downstream node, whether it's a BMP or a junction. And then we start to connect those nodes and junctions together. Is there something downstream of that BMP? In this case, it's just the outlet. We also have the untreated node going to the outlet, but because the untreated node is not in here, it's not really doing anything. So it's sort of redundant. You could take this out and the model would behave exactly the same. We keep it in there just because sometimes we use it. And then always the final one here is whatever is the most downstream needs to go to 0. So this is sort of a dummy row, but Sustain uses it just to know that the model has an outfall point. So out goes to 0 by 1. Outlet type, it does get a little more complicated here because we shouldn't spend too much time on this, although we could spend a lot of time spending time on this, but How do you train? So this is where you do treatment trains. So let's add some space in here. I'm gonna put this here. I'm gonna start making dummy stuff. And it looks like, John, you're doing it too. There's that East LA, he's got untreated. And that's what it looks like now. But let's say we want to add something. And I'm gonna add, there's a cistern, and I'm gonna just name it what it is, cistern. And then there's bioretention. This wouldn't work because I haven't introduced these in 7.15 yet. This is presuming I've already done that. And I've done everything right upstream. I've already characterized the cistern and the bioretention. So if I wanted to add those to the routing network, I would do this. East LA is going to go to the cistern. Downstream of the cistern is the bioretention. And then downstream of bioretention is the outlet. Oopsie. So now I've got a train of BMPs. It can get even more complicated than this really quickly, because what we're saying right now is we've created additional nodes, as John's drawing here, for these other BMPs, and that's all fine and well and good. But what if I want my orifice flow, my release type 4, which is representing my sewer, what if I want that to go to a dummy node? Right now, if the cistern is the BMP that has, well, let's stick with East LA project. If East LA project has that release type 4, and I'm putting, like, let's say 3 CFS down to a sewer, and that's what I want to do, I can't use 1 anymore as the outlet type, because I'm taking all of the things leaving the BMP, whether it's weir flow, overflow, underdrain flow, untreated flow, all the types of flow leaving the BMP, it's all going down to the cistern when I use 1. But I've got this sewer functionality that I want to use, so I've got to repeat this a couple times. I can't use total anymore. I have to use 2, 3, 4. Oops, sorry. It is doing things I don't want it to do. 4 and now 5. 5. And so anytime I want to start getting a little more detailed in terms of, well, I don't want my underdrain flow to go down to that BMP, because that treated flow is just going to dilute what's going in that BMP, and then it's going to get treated twice. And sometimes that's happening in reality, and sometimes it's not. What you want to do is figure out, how do I represent what's happening as implemented? So in this instance, I've taken what it was before, which is this, and I want to add more granularity. I want to add more options for outlets. That means 1 goes away, and I break that out into 2, 3, 4, 5. And so the weir flow is just, John, that's just the overflow from the project. Is that right?
That's right.
The outlet type number does matter, is a question from TJ. 2 always, when you have 2 as the outlet type, that means weir flow, which is overflow. And let's say we want to go down to the cistern. That's fine. Everything is going to go down to the cistern except for orifice flow. This is going to be dummy. You have to organize near the top point to where it goes. Yeah, exactly. So in this case, I've got 2, 3, 4, 5, which are all my options other than total, which we're not using anymore. And everything is still going down to the cistern downstream, except I've got this orifice flow, which is that release type 4 that we're using. And now we're sending it to some dummy node. And again, I haven't introduced that in 7.15. So if I did this, sustain would give me an error. Let's presume that I've created this dummy node. And now I'm sending water at it at, I think, 3 CFS, whatever I specified in card 725 before. And now water's leaving the system, and it just kind of sits there at this dummy. It doesn't do anything, because I'm going to evaluate at the outlet. And so all this water, again, is going to the outlet, as John's drawing here. Really glad you're drawing this, John. It's hard to explain it and describe it in the card and show it at the same time. So we're still evaluating at the outlet. The outlet will never see this dummy flow. And so that's great. That's exactly what you want, because that's what's happening in you know, these projects where you're saying, let's take 3 CFS and push it to was it Donald Tillman? And it's going to disappear from kind of the stormwater infrastructure in a sense. It goes away. It's going to be used for purple pipe or something. We don't know. And so this is how that's handled. So let's say this is that question earlier is, how do I do discharge to a sewer? You specify release type 4. You specify the flow rate in card 720. You introduce a dummy node in card 715. And that's just a place where water goes and you don't have to think about it. And then you have to make sure that flow pathway, this 3 orifice, goes there. And that's it. Now we're simulating a diversion to sewer at that specified rate. Complicated question indeed. We don't have an easy way to do that.
Yeah, that's interesting. We have done that before, using the cistern feature. So what you would do is you could specify a dummy node and then use a cistern, because a cistern allows you to specify a diurnal distribution of when water gets diverted out. And we touched on that just briefly in 725, but that's one of the options, is you can specify that you're using a diurnal rate of discharge, and then you calculate, it depends on the number of people, and then you put a per capita rate, but whatever it is, you can translate it into the rate at which you're diverting out of the system, say 12 a.m. to 8 a.m., and then have it just release at that point from there. Another point that I want to make on here is, let's say you want to know what the total benefit of this is. In reality, you can't measure it only by looking at what you see at the outlet. So in some cases, you could define sort of this virtual outlet somewhere over here, where you would take the dummy outflow from here together with the outflow from here, and then you would evaluate what's my total load reduction or my total concentration, whatever it is at this point. It's not a real point because this is actually at a treatment plant. And this one is the outlet of your network. But you could define a virtual point where you can send 2 of these outlets. The world is open, and however, it's just why I would describe it almost like a Lego box. You can put these things in the way that you need to represent them to answer the question that you're trying to answer.
Oops. So yeah, I kind of just did what John was describing. Well, now what we've did is dummy is going to go to this virtual node, and now outlet goes to a virtual node. And so you can set your assessment point at that virtual outlet node, and that will tell you everything that's in the system is being accounted for there. And without getting too, philosophical, what John was saying about, whatever you imagine, whatever system you have, like, this is where it happens. Like, oh, I've got all this crazy routing, or I want to do this in terms of moving flow here and there, and underdrain goes that way, orifice flow goes that way. This is exactly where all that happens. And it can get really complicated really fast. You can accidentally do circular routing. Sustain will give you an error for that. Like if you route East LA to Cistern and then Cistern to East LA, Sustain will stop you right there and say, no, that you can't do that, because that's water is just spinning in circles. And it gets really easy to do that as you start to add these things. So the last thing I'll say about this is that, because we are running out of time, what we had originally was this. East LA was going to Cistern, and then we started to change it and say, well, now there's 2, 3, 4, 5. This is actually the same thing as what we just had when it was East LA going to Cistern by 1. Now we've done 2, 3, 4, 5 is still going to Cistern. All the same flow from all the same places are going to the same place. Now we're just doing it in a different way. But if I want to change one of those things, that's where we do that, is changing that downstream node to something like bioretention or dummy. I think that's what it was. Okay, again, we could probably talk a lot about that, but we gotta stop somewhere because we only have so much time left. Optimization controls, since we're not doing that here, we're just gonna skip it. If and when there's ever a future presentation, we'll probably get into more details there. Cost functions, that's really for the optimization. You could do it for a single solution run, but the size isn't changing, so the cost isn't changing. Diversion structure cost, again, it's just another cost function. We're going to skip it because we're probably not going to be, since we're not optimizing for diversion, there's no change in cost. 810 is adjusting your variables for the optimization. Since again, we're not doing optimization, we're just going to skip on right by it. And now we're at the last card. I bet you're all really excited to talk about the last card and move on to the next thing. So now we've defined, routing network, drainage area, connections between the BMPs, what the BMP looks like. Is it diverting to the sewer at a fixed rate? Is there under drain treatment? All those things have been configured. The last thing is setting the assessment point. And there's you can see all the comments for this one. Gosh, look at this thing. This is really long. There's a lot going on here. There's only a few things that are really important for what we're doing. One is you can add several lines here to get different pieces of information. So this first line says, I want to set my assessment point as the outlet, which is, or it's defined here as out, but that's the final node in the network as it was originally drawn. I want factor group 1, which is my pollutant ID. So factor group 1 in this case is total suspended solids. My factor type is my evaluation factor. So really all I'm doing is going up here and reading these things. And that is average annual load. So what this is saying is tell me at the outlet what average annual load is for total suspended solids, and I'm going to call it total suspended solids. These other things, these are for optimization. The -99 indicates that the model will, or sustain will skip these. So you don't have to worry about these. It's really just about these columns here, and then this final column is a name that you define. So this is pollutant 2 for average annual load reduction, pollutant 3, pollutant 4, pollutant 5, pollutant 6, pollutant 7. And then since I know all of these in order, because it was defined in that card 710 before, maybe even 705, I know that pollutant 1 is total suspended solids. I know that pollutant 2 is total nitrogen, total phosphorus, so on and so forth. And so these match up here. And I'm doing average annual load for all of them. There's other things you can do here. Average annual concentration. It can get pretty fancy pretty quick. I don't know if you'll all be using that anytime soon. There is another type of factor group here, which is -1. So that means you're not doing a pollutant anymore. You're doing a flow related factor. And so I've got 2 flow related factors, -1 and -2. I go up here to factor type. We're going to output average annual flow volume and peak discharge from the model. And so I know this is a lot of like numbers to get things that you want, and I always have to go up and read this again and again. The important thing is that define your assessment point. Where do you want sustain to output, the output, or at what point in the nodal network that you've created do you want to provide output? Well, that's the BMP site. I wanted to do all of my pollutants. I wanted to do it average annual load. These are my names for it because these names will just go into the outlet file or the outfall file, output file. And then I also want to do the 2 flow factors, my average annual volume and my Q peak. And again, I've got names for those to kind of remind myself what those are. And so here, you can add every node in your network. You can set assessment points everywhere, and the model will output at all those places these factor types and factor groups that you specified. John, I feel like there's stuff you want to add here to this one.
Oh yeah, this is great. This is where you are saying what you want to evaluate. Now, notice this outlet. When you output at the outlet, the only thing that you can see is the total flow that came out. I wish I hadn't erased my network, but if you decide to output at East LA itself, you can also do that. And what that gives you then is, if you wanted to see the time series coming out from East LA, it would actually show you the time series through each outlet, through the orifice, the weir, the under drain, all the different outlets. If you specify, the actual outlet here. Outlet, because of the fact that we're already downstream of East LA, it's just going to show us the total flow that reaches the outlet. But yeah, you can get as detailed as you want, and then when you drill down deep, you can get evaluation factors or time series outputs. But the time series for each of those outlets, you can output that for each BMP if you want, just by specifying each of those locations and defining the terms that you want here.
So what I did here while John was essentially what John was describing is if you want to know what's happening at BMP site East LA project at every hour and get that time series, all you have to do is add it here, and now you'll get the output here as well. And so if you want to me, if I was someone who hadn't used Sustain and was just starting, I would be adding probably every node in my network just to confirm that I understand what's happening, because we only use outlet or the final node is because we generally understand all the connections that are happening. But if you want to confirm, how do you know that 3CFS is actually going to that dummy node? You would have to put that in here and see that. So if you wanted to see the dummy too, you could just do this and add dummy. And now you'll get a summary file with all these, but you also get the time series. And so if you open up the time series for that dummy node from the output, you should see a hydrograph that's like cut off at 3CFS, meaning it gets flow, but never more than what it's supposed to. And then it'll stay flat until that time series, that runoff drops off from the storm. So that's what you would see at that dummy node. And if you have multiple things going in there, it gets a little more complicated, but if it's just one, that's how that works. So with that, that's our input file teardown. We didn't get to everything because there's so much to talk about. I apologize, we don't have 8 hours. I wish we did. As much as that would be painful for probably all of us to sit down and do this for 8 hours. The next part is, we've already done that. Well, I guess we can talk about these things really quickly. There's a number of common errors that happen, and we'll go through these really quickly. The input file is tab delimited. If you start to do double tabs or spaces instead of tabs, Sustain will have a problem. And you just have to make sure that you're always tab delimited. As we showed earlier, C as the first character line is a way to indicate that something's being commented out. So let's go back to this. Let's go back to this file. If I call the node, so if I'm going to introduce a new BMP and I'm going to call it cistern, that's a problem because it starts with a C. You can't use that. You could use maybe like I don't even know if you can use it. I think you can use an underscore. I might just use a different letter altogether. Just do A underscore cistern, something like that. Because as soon as it has a C, Sustain won't read that line anymore. It'll just skip right by. So you have to be careful with using the letter C. And that's only the first character. You can have a C in whatever word you're using. It's just the first character can't be a C. I one time ran into a problem when I was making my names too long, so East LA median project, if I made that 50 characters, that's going to be an issue for Sustain. It just doesn't make room when it's creating that input file and making the run to do that. folder directories, that happens all the time. What we described, I'm going to go back over here. What's happening up in card 700, these, I get these wrong almost every time I make a run. Like I've got it pointing to the wrong place, the directory doesn't exist. That's really common, and that's, you know, that's a pretty easy fix. You just make sure that the directories you're pointing to exist and the right data is there, and you'll be fine. No spaces in the folder pathway. This is kind of a funny thing. I don't remember exactly why this is, but let's say my folder was named LSPC space data. Sustain doesn't like that. You have to have non-spaces throughout the entire folder pathway. And you'll notice that we use underscores instead of spaces. So you'll have to do the same thing or just use, you know, no spaces at all. So that's that. Make sure that there's no spaces there. Dates and time steps, just making sure that whatever is in the HRU, whatever you want to run for your simulation, that you're updating the dates and the time step to match. So it's almost always hourly time step. And whenever the storm or time period that you want to start and end, excuse me, is starting and ending, that matches in the input file that you're creating. Circular routing, we talked about that. Sometimes, you know, you get a complicated network and you don't realize that you're kind of just moving water in a big circle. Sustain will throw an error for that, and it'll tell you if you have that. So you want to be careful of it, but if it does happen, Sustain will give you an error. And the last thing I'll say on these common errors is investigating the time series output. To me, being a strong modeler and a strong user of Sustain is being able to look at the output and understanding what's happening, because that's how you understand if things are going wrong. Like if for some reason your under drain pollutant removal isn't working, you don't know that until you look at your model output. The same thing with the discharge to the sewer. If for some reason it's not ending up at the dummy node, you have to look back at your input file and maybe you kind of put the wrong value in, or you put a different node in and you didn't mean to. Like clerical errors like that happen, I would say pretty regularly, because there's so much happening here. It's easy for something to get lost along the way. So being able to set up an input file is one thing, but being able to check and be confident that the output you're getting, like the summary output that you're getting, that, you know, on average 20% load of zinc is being reduced by this BMP. How do you, the way you know that's right, and the way you know you're confident about that, is you can go into the time series output and see that happening hour by hour and do the calculation manually. And I'll show you a little bit how to do that. It's really just in Excel, so it's nothing too fancy. File size, if you're running low on space on your C drive, I don't think you guys are going to get this issue. I had that problem once. We were running a big model and we ran out of space, and that broke the model, as you can imagine. And then Notepad++, we've mentioned that before. That's kind of the program of choice to do editing. So with that, let's say we've got I'm probably going to get out of this altogether, because I think we can just go start running the model. Let's say we've got an input file that is ready to rock. I'm going to go over here and go back to where we were before. These are all my other models you can see. Sustain, and this is just getting back to the kind of folder structure that we started out with. I've got all my input files, I got my batch files, this is how we run it, and this is where the output goes. So, so let's say we've got our LSPC data all accounted for. That's the HRU runoff time series. My input file, I've characterized the BMP that I like. It's in there. Let's run this one first, the 85th percentile storm. If I want to do that, I use a batch file, and these are all my batch files that I created, and I've named them just to kind of remind me of what's inside. And so the batch file isn't anything too complicated. It's a set of instructions for the computer, and it is composed of 3 parts. The first part is, what am I running? And the answer is you're running Sustain, and Sustain is here on your C drive because you've placed it here in this folder. And so I can actually go over there. I can double check that it's there. Go back one more. Model, boom. My sustain executable and my sustain DLL are as I've indicated there in the instructions. The next one is the run type. We always use 0. Well, you're always going to use 0. Sometimes we'll use different ones because we're doing optimizations or we're doing different things. You guys will always want to do 0 because that gives you all of the output that's available for the model that you're running. Sustain won't short circuit anything. So 0 is the default for you all. And then the last thing is what's the input file we're running? And so again, I've got the folder directory here with the file. So if I go back here, current input, this is what I'm telling it to run. And so that's all there is there. There's a pause and exit, and that's just because we're going to open a command prompt with the batch file. And it'll show us running it. So so everything, I've created this before and everything's going to run smoothly because I confirmed that it was. So all I do is double click on the batch file and it runs, and the volume is really loud on my headset. So that was a really loud ring. I don't know if you all heard that. And since we're running an 85th percentile storm, which is 3 or 4 days, it runs really fast. I created a couple different input files for you all to play with. I won't be able to get into them in detail because we have only so much time, but I have an input file. Actually, I have a README for it too. So if you want to know what all these are, it's just different versions of the first one. So the first input file here is running 85th percentile storm with the diversion rate as specified, which is 8.09 CFS, I want to say. This one _online is the same exact thing, except now we're running it without a diversion rate. So it's an online facility, so it's not restricted. And so that's just to show like, well, what if I do this? What if I do that? And this is kind of getting to what John was saying earlier. The model is whatever you can imagine and make it up to be. And so if you want to say, well, how much better is performance if we just pop off that diversion rate and kind of throw a direct line at this BMP? So I ran a model to do that too. I have a couple broke models that I broke on purpose to show you all what some of the error input looks like. So you won't need to run those, but I'll show you what that looks like. We also have a continuous time series. So I think in this one, we're running it for 30 years. It's the same thing as 85th percentile storm, but I adjusted the dates to be longer, and we're reading in a different unit area time series from LSPC. So this is a long-term continuous time series from January 1990 to May 2020. It's pretty big in terms of time series. The teardown is also in here. We just went through that. And then I have a couple optimization ones in here. Since we're not getting into that, I'm going to leave those there. But there's that README that explains all these, since I can't get into them all in detail. And again, if you want to see what's going on in here, it's just a matter of opening up Notepad++. This is the same thing as what we saw in Excel, except it's a little more text file looking, and that's okay. If you want to, again, if you want to change things, it's as simple as going in here and changing things. So now weir height is not 22 feet, it's 12 feet. I'm going to undo that and get out of here. To me, the last important thing that we can talk about is the output. So let's say we've run it. You're going to get a bundle of output folders. So let's go to the output file that we just generated. It's going to be the 85th. And you notice that I changed the names for the output to kind of help myself remember what is the input file that this came from. You actually don't know unless you go back to that input file and see the directory that you saved it as. So this is what output looks like. You get two types of files. Let's see if I can get these to organize nicely. Yeah, here we go. So you get two broad types. There is your summary files, which are really small, and we can open them up. There are .out files. I have my computer automatically open them up in Excel just so I can do things or do math on them really easily. I generally recommend you guys to do the same, to set the default to Excel. because all it does is output this little summary. And so what this is saying is, these are your assessment factors, and this is the value for those factors. So the model output 6,700 pounds of TSS at the outlet. And if I had more things down here, this would fill out longer and longer and longer. So for example, if I did East LA medium project, these things would repeat for that there, and we would have different values for what was happening at that BMP. So this tells you what's going on here. It's average annual load, and so this is always in pounds. Average annual flow volume is always in cubic feet. You can see it's quite a huge number. You'll generally have to convert that to cubic feet. Q peak is CFS, so that's generally what we use as a conventional unit, so there's no need for a conversion there. So this in itself doesn't tell you much. It gives you a bunch of pounds, and you're like, okay, cool, what do I do with that? Well, now you have to compare before and after. So post-dev is short for post-development, and that's your existing condition run. So let's say you run sustain as we just did, and you want to know what it is, before the BMP. That's post-dev. I'm gonna, try and get this to do, I was gonna try and get it to do a half U. And so these are those values for the no BMP condition. And then in it is, let's turn all the BMPs on. And so you can see there's a difference. I've got 8,800 pounds without BMPs for TSS and 6,700 pounds with that BMP in place as it was modeled. So we're doing maybe 25% reduction. And you can do, because this is Excel, you can do, big minus small divided by big to get your percent removal. So 23%. That's pretty good. And you can do that on all the numbers. You can see that some of them aren't very big. It doesn't, I may be doing something wrong here in terms of the values, but that's generally what we do is a comparison of before and after. So that's the summary output time series. I don't really recommend going to the summary until you have your results, or until you're feeling really confident about your model and how it's performing. These other types of files, these are your time series files. So these ones down here, the post-dev eval is the summary of what's happening. So if I sum up all the load, that's that value for TSS. But if I want to know, or if I want to dig into the model, and again, this opens up in Excel, this is this file that helps you see the time series. And this file is a mess. We could spend 4 hours just on this. But the short version of it is all of these headers pertain to, and I'm going to do a transpose here. It might take a minute to think about it. Pertain to all these columns going across. And so if you want to know, hopefully that will unlock soon. There it goes. And I can blow this out entirely. So all these are just a listing of the headers, and then I just placed them over here because it's a lot easier to see and know what the heck is going on. So you've got your date and time here, your BMP volume, your water depth, inflow, weir outflow, orifice channel flow, under drain flow, all of the different avenues and all the different motions of water and pollutants are being tracked here hour by hour. And so this is when we were saying earlier about being confident that your model is correct and water is moving when it's supposed to move to these different nodes and BMPs. This is how you jump into the model and see that. One thing that I think is really important here, well, there's a couple things. Sorry, I'm flicking around a lot. All your flow items are kind of up front. At the end, you start getting into your pollutants. So this is pollutant 1, and all the different things: mass in, mass out, mass under drain, pollutant 2, pollutant 3. So again, it's using that same pollutant identification where pollutant 1 is TSS, pollutant 2 I think was total phosphorus or total nitrogen, and so on down the line till zinc. And so you're tracking every drop of water or every cubic foot of water, every pound of pollutant in the flow that's moving all that around. And so being able to open this up and figure out what the heck is going on is really helpful. And so Excel is great for that. It'll give you the hydrograph for your total inflow. So this is the inflow going to the BMP before and after. And so you'll notice there's a lot of extra time at the end here that we run the model. We don't necessarily need to. All the water's passed through the BMP. So this is your inflow to this node, which is the outlet node. What John was saying before about, what John was saying before about what we're outputting, and I closed that spreadsheet, but this is only showing flow and time series at the outlet. If you want to know what's happening, which I think you all should, what's happening at that project, you would need to specify that in the input file. And once you do that, it will show up here. So notice that this is labeled out. And that matches with our input file name for this node. So if I go back in here, this will open it at Excel again. That same name is here. And so if I just change this to, we can do this really fast, I hope. I'm gonna change this to this. Oh no, I can't do it in Excel. That's right, darn it. Okay, well, I won't do that. But in any case, if I wanted to change my assessment point or add an assessment point for East LA project because I want to see the time series there, I would just make that change in the last card of 815, rerun the model, and it would output that right to here, right in that same place. And so instead of out, it would say East LA project, I think is what it was, something like that. And that would give you all the flow time series and load time series happening at that place. I have some, so I kind of made some plots for this. And so one of the things that, we just looked through this, what that time series helps you do, and what this evaluation summary time series helps you do, is make these plots. And so this is exactly what I just showed. What's the post dev, which is the existing condition, flow going to the outlet. So that's under the current condition with those HRUs. Well, if I add that BMP at the 1 acre footprint, 22 foot weir height, and all these other parameters, that's the init. And so I can plot that time series right next to it. You can see there's a reduction because that BMP is taking water and infiltrating it to the subsurface. And it's a big BMP, it's doing a lot of work. So that's kind of one way to display your output. The other thing is the summary, which we just talked about. And usually I just do bar plots for that. And so this is the volume in acre foot at the outlet for post dev. And then this is the init summary file, which shows that we've reduced volume by a pretty good margin, over 20%, down to about 100 acre feet with an 8 CFS diversion rate. I did run kind of another version where I said, well, what if this thing's online? How much better can it get? And so you can see that post dev, of course, stays exactly the same. It's not changing. The pre-BMP isn't changing. Instead, the just this post or this proposed condition is changing, and it's called init because it's the initial BMP run or the initial BMP output. So apologize that we went through this really quickly, but hopefully it's given you all kind of the foundation to say, all right, well, I know how to make adjustments to my input file. I can change the dates. I can get a different input time series from LSPC to make it long-term or 85th percentile storm. You have all of these input files that do that. So 85th online, you have the teardown that we did. You have a couple of these broke ones, and I'll show you what those do real quick. So if I want to run, I purposely made errors in the input files just to show you all what it looks like. So if you get an error that looks like this, it's because in card 700, there's an issue with the LSPC land put time series that you provided, or that's being provided there. So you have to go back, look card 700, make sure it's right, and then rerun, or save it and then rerun. So that's what that error looks like. There's another error. This is for, it looks kind of like garble. Actually, doesn't give you a good error. It says you're writing over protected memory, which is not true. This is saying that there's something wrong in card 710 where HRUs are defined. So that's probably just a clerical error happening there. So you want to just go back and confirm that nothing's happening there. This one is where I have this batch file, but the instruction I gave are wrong. Like I gave it the wrong location for where sustain is. And so what the command prompt says is I can't find that path that you specified, which is true because I made a oopsie here. And if I do a control save and run that same thing, I think it'll run, or it'll get further past it. There we go. And so now it runs. And so the last thing I want to do is mentally prepare you all for the number of errors that you're all going to get for when you run sustain. I get them all the time, and I've been doing this for a number of years. John's been doing it for longer than me, and I'm sure that John runs into errors sometimes too. And it's just because there's so much happening. It pays to be slow. It pays to be really methodical in what you're doing. If the faster you go, with the certainty that you'll bump into an error, it just becomes that much more certain. So be slow and be careful. Yeah, I guess those are kind of the same thing. Anyway, that's essentially the main part of the training session. We've already done this model execution. There is this alternative exercise that we created. John and I kind of had this side ulterior motive that wouldn't it be great if this training went so well that TJ's like, you know what, we need another one. Tell us more about sustain. And we're ready for that. So whenever you guys want to talk about how to change your management objectives, like are you looking at flow, volume of flow, Q peak, that there's kind of a, we've already kind of thought about that. And so you can change in terms of whether your management objective is pollutant load or volume or flow. And that's in card 815. At the very end, the last thing we talked about in that file teardown was those things. And so we actually already kind of went over those a little bit. Changing the decision variables, even this we've talked about a little bit in terms of under drain treatment option, maximum effluent rate, routing, nested BMPs, and so on. This could take a long time, so we didn't get into that. Changing your assessment point. We talked about this a little bit. Is your assessment point at the BMP? Is that where you want the evaluation to take place? Or is that a downstream location that maybe there's 5 BMPs upstream of, and you want the summary and the time series at that place? There's also basin-wide versus jurisdictional. This, of course, gets really complicated because sometimes you may have different cities involved. So is that consideration? There's also the optimization, which we didn't get to at all, but is a whole other avenue of discussion. So there's a whole other world that we'd love to talk about if that's ever of interest to anybody. There are useful resources. So if you Googled EPA Sustain User Manual, you'll get a little bit of help there. We've also created these documentation for WIMS on the repository. So we'll go to that real quick on the side. So those are there all ready for you all to download. Last question from TJ, how would you size a dry well? I guess it depends on what you mean by size it. Like in terms of like dimensionally, what would the dimensions of a dry well be? Or how do you size it in terms of an optimization? Like, do you want to size it? Should it be 10 or should it be 1 or should it be 100? So go ahead, TJ.
Yeah, just the dimensions. When you put it in, how would you put the dimensions in?
So that's a good question. Like the standard that I use is if it's a 50-foot dry well with 1 foot sleeve, and we have this on the WIMS documentation actually. It's a 50-foot dry well, let's say, and it's got a 1 foot gravel sleeve and 2 feet of gravel underneath. We did the math on this a long time ago. All that space, if I pulled up that space, that's actually about 62 feet of ponding height across like I think it's like 4 by 4 footprint. Don't quote me on that. We do have that in the utility documentation. But yeah, essentially you would put it into like an equivalent size. So yeah, the way I think of it is let's take all that volume and put it into ponding, because there aren't that many sort of infiltration processes dynamics at play there. And as long as I have the volume right, then that's really all that matters. The infiltration will actually matter as well. So if you're going to be using an actual infiltration rate and infiltration surface area, then you can't use a small footprint anymore. You probably want to use a big footprint. But again, there's some details there that if we had more time, we could get through. So apologize, I can't get into more of that one, but I guess what John was saying earlier is that you really get to kind of decide how this input file is configured. And if you're not sure how something works or how something operates, you can just start making changes, run the model, see what happens, and just kind of keep playing with things. And the more you do that, the more you'll get a sense for how the model's operating and how to change things to get things to cooperate as you're intending for them to do.
Well, thank you, John and Ryan, for guiding us. I'm sure we'll watch this video 10 more times to figure it out. And I encourage everyone, next time you guys have a project that you want to run WMS for your PCRs, try using Sustain and let us know how it goes. And let's see what issues we run into, and we can learn from one another. So thank you, Ryan and John. And if you guys have any other questions, you can shoot me an email and I could forward it to John, or let's try to figure it out together. Thank you everyone for coming to the meeting and hanging in there for all 4 hours. Thank you, everyone.
Thank
Thanks,
you.
everyone.